morning, good afternoon, and good evening. So welcome to the 14th International Symposium of Reservoir Wettability and its effect on oil recovery. My name is Tina Puntervold. I'm Associate Professor of Reservoir Chemistry here at University of Stavanger. And I'm also the Deputy Director of the National IOR Center of Norway. With me, I have my colleague in the Smart Water IOR group, Associate Professor Skule Strand. He will be hosting the Wettability Symposium with me today. And with us also on the computer screen is postdoc Alexander Mamonov, who will take care of the questions during the Q&A sessions several times today.
In 2018, Professor Mahani hosted the 13th Wettability Symposium at University of Texas in Austin. When he invited for someone to take the baton, Tina and I thought that it could be a good idea to host it in Stavanger jointly with the IOR Norway 2020 conference. Unfortunately, as we well know, the COVID pandemic hit in, and last year's symposium had to be postponed. So today, the 14th Wettability Symposium will be held digitally, and hopefully it will be the one and only digital Wettability Symposium. So let's hope we can meet somewhere physically for the 15th symposium next year, or maybe in 2 years' time. We'll see.
Due to the conference being digital this year, so instead of flowers for the presenters, we have instead decided to donate 10,000 Norwegian kroner, which is about $1,000, to the UN UNICEF by buying what they call is a world gift. So it's a gift card for the UNICEF, which is called School in a Box. So School in a Box, we have bought 6 of these boxes, and these boxes contain all the stuff that a teacher might need to teach children whose schools have been destroyed or closed down for several reasons. So we take the opportunity to thank all the presenters and for their contributions, and all the people in the evaluation committee for their willingness to review the abstract sent in 2019 and 2020. So we are soon ready to kick off this symposium, but first I want to notify you that this symposium is being recorded for the use and for publishing on the IOR Center of Norway website, and also at the University of Stavanger YouTube channel.
We have 2 main topics of today. Fundamentals, it will start now, and will last until 15:30, followed by core restoration measurements and modeling of wettability until we end at 17:30 Central European Time. There are 3 to 4 presenters in each session, and please note that we will have a joint discussion at the end of each section when the last presenter has given his or her talk. To ask questions, you can write your question in the chat during the talks, and please state whom the question is for. I will now let Tina start the first section.
So in this symposium, we will focus on the main factors affecting reservoir wettability and how the wettability could be described or measured and optimized also during core restoration procedures. We are looking very much forward to this section and to this symposium. and we're looking forward to hearing about the new ideas and the new research performed around the globe from our colleagues. The first section will be on the fundamentals. And so Alex will then take care of the questions from that section at the end of the section. I have the pleasure of introducing our first speaker today, who is Patrick Brady. Patrick Brady works at the Sandia Laboratories. He will present electrostatics and oil recovery from tight formations. Patrick Brady is a senior scientist at Sandia National Laboratories. He's been at Sandia since 1993 while serving as an adjunct assistant professor of civil and environmental engineering at New Mexico Institute of Mining and Technology in Socorro, New Mexico since 1998. Before Sandia, he was an assistant professor in the Department of Geological Sciences at SMU in Dallas, Texas. His research interests are in the fields of water treatment, contaminant chemistry, enhanced oil recovery, nuclear waste disposal, and climate change. So please, Patrick Brady, go ahead.
All right. Anybody can run an international conference when times are calm, when the waters are calm. Only Tina Puntervold, Skule Strand, and the National IOR Center of Norway could succeed when there's a global pandemic, an international travel ban, and oil market turmoil all occurring at the very same time. So hats off to Tina, Skule, and their team in Stavanger for putting together the 14th International Symposium on Reservoir Wettability and Oil Recovery. This symposium that Norm Morrow and Jill Buckley put together long ago has been a fabulous accelerant of technical advance in wettability. Having the symposium in Stavanger is more than fitting because the Stavanger Research Group has been a leader in wettability for decades. Many of the concepts I will discuss in the next 8 minutes were pioneered here in Stavanger. 3 in particular I will touch on are carbonate surface chemistry, the observation that under certain conditions, high sal is better than low sal, and how to apply the smart water concept to tight formations, an area of emphasis here in Stavanger. Let's go to slide 2. We're doing screening calculations for 3 tight formations in the United States. I will focus on the Eagle Ford in South Texas. The reservoir is made up of calcite, illite, and quartz. In each situation, our goal is to identify the fracwater chemistry that makes the respective formation most water wet. This is a sharp difference from existing practice, wherein water is bought as is, typically from a farmer, and all that water must do is carry proppant, maybe keep a polymer stable, not scale, and so on. The smart water we hope to design will do all that, plus shift the frac formation to water wet. Let's go to the next slide, slide 3. We do this with the bond product sum, which we developed 10 years ago as a measure of electrostatic forces for adhesion. Others have come up with alternatives and improvements. They all aim to do the same thing. Use the measured surface charge of the oil, the reservoir, and the connate fluid to assess and then alter wettability. They are all built on surface complexation models for oil and all the minerals. We have surface complexation models for calcite, illite, quartz, dolomite, but not one for kerogen, which is okay because oil adsorption to kerogen is probably not an electrostatic thing. It's probably a hydrophobic bonding thing. The surface complex models that we do have are described in the literature. One thing that is not described there but is new here is the process by which we add up the surface complexation for the individual minerals to estimate bulk rock wettability. In the case of the Eagle Ford, that's calcite and illite. Let's go to slide 4. The right-hand side of this figure shows a correlation between spontaneous imbibition oil recoveries from Eagle Ford cores measured by Valeria in 2016 as a function of brine composition, plotted against our independently calculated bond product. What you see is that greater recovery goes with lower bond product, as one would expect, and you get a nice linear correlation down there. If you look at the left-hand side, this shows Valeri's contact angle measurements versus brine composition. He did it with sodium chloride and calcium dichloride. And you see how contact angles drop and water wetting occurs. There's a dip there in the middle, about 5%, and then things go back up. The bond product calculation predicts into the dip, and it doesn't get the other thing. And we think that's because there's probably complete collapse of the double layer. And my colleague Joel Tete at the University of Kansas is working on this, and others are too. For the Eagleford, though, the surface complexation models work well in the salinity range we're looking at. Once you get above 100,000 ppm, things get tougher. And we think the reason for this is that the increase in water wetting prompts countercurrent imbibition. The water wetting is a combination of, again, calcite and illite, and you'll see it in the next slide, where we try to design a smart water for fracking. And we do this by simply changing the water composition in the bond product calculation until the bond product reaches a minimum. And then we make certain that the new frac chemistry isn't expensive, hard to work with, or likely to cause scale. An example of this is shown in the table. For the Eagleford, the connate condition is mixed wet. Introducing fresh water makes it more oil wet. And you can see why. Basically, lower sulfates in the fresh water increase the calcite bond product. The sulfate effect was pointed out by Tor Osted long ago. Lower salinity increases the bond product as well. I believe this was also pointed out by Tor. If you look at the trend going down, some salts are particularly effective at decreasing the bond product, others are not. And what we do is essentially just put in random salts to see and punch a button to see where the bond product goes. And we stop when it gets fairly low. Once arriving at a smart water composition, we want to verify and possibly tweak the recipe experimentally. Flotation tests are a rapid way to do so. Core floods take longer, but give more information about transport aspects. An important point here. Oil recovery from the tight formations, it's a combination of chemistry and water transport. Transport due to, for example, osmosis. The bond product calculation only gives the chemical side, leaving the transport side free. But the fact that there's a strong linear correlation between the bond product and oil recovery seen in Valeri's measurements suggests that the transport aspects are not large, at least in this case. So the bond product gives an estimated increase in oil recovery. In slide 6, I use that to project the financials of field implementation. There's a graph that shows 10-year baseline financials and the financials for smart water huff and puff in year 4, and for doing using the smart water in the original frac. NPV10 is the net present value over 10 years. The key point of this example calculation is that using a smart water in the original frac makes more money than doing it later in a huff and puff. I'm out of time, and with that I will close. But I leave you with the fondest hopes that we'll all meet again in person soon, and that you will all remain healthy in the meantime. And thank you again to Tina and Skule and their team for giving us all the opportunity to be together again today.
Thank you, Pat, for the very nice and kind words. And also, of course, thank you for the interesting presentation. I will remind people to put questions in the chat. Please write whom the question is for. And we'll take the questions together in the Q&A session at the end of this session. So the next speaker today is Zahra Aghaeifar. She's from University of Stavanger. Her presentation is Importance of Capillary Forces During the Low Salinity Water Flooding. Zahra recently graduated with a PhD degree in petroleum engineering from University of Stavanger. She has a specific interest in reservoir chemistry and smart water flooding as an IOR method, and how the different parameters affect both initial wettability and wettability alteration processes. Her PhD thesis was about smart water flooding in sandstone reservoirs at high temperature. And also, in addition to smart water flooding wettability knowledge, she has also knowledge from asphaltene precipitation, because she worked with that during her bachelor and master thesis in Iran. Please, Zahra.
Thank you, Tina. Hello, everyone. Good afternoon. I hope that you enjoy my presentation. As Tina introduced, I'm going to talk about importance of capillary forces during the low salinity water flooding. As everyone knows, low salinity is a smart water. It's a brine made by modifying the ion composition to alter the wettability of reservoir and increase the oil recovery. It's very easy to implement, no expensive chemicals are added, and it's an environmental friendly method. In sandstone, often low salinity brine is the smartest brine compared to the other brines. How does it work? Actually, smart water improves the wetting properties of oil reservoir and optimize the fluid flow and oil recovery in the porous medium. Several mechanisms has been suggested by different researchers, but the general agreement is that it increases the water wetnesses of the reservoirs. We know that by increasing the water wetness, actually we will increase the capillary forces that will help to the smart water brine to imbibe to the smaller parts, which is already bypassed by the high salinity brine. Thus, we will increase the microscopic sweep efficiency. We know that in sandstone, initially, we have negative charges on the surface, and especially the most active surface is the clays. So this negative charge has to be compensated, and initially we have equilibrium between adsorbed polar organic components from oil and also cations from the brine. So when we introduce the smart water or the low salinity brine, active cation has tendency to dissolve from the surface. Therefore, the negative charge on the surface has to be compensated, and the proton has the highest affinity to adsorb to the surface. Then we will have a local increased pH. This increase in pH will help actually to the polar component to dissolve from the surface. What I explained is summarized in the two sets of the reaction. The first is desorption of the active cations by smart water, which is a slow reaction, and that's the controlling reaction. And the second set of the reactions are the wettability alteration, which are ordinary acid-base reactions. We all know that the oil recovery forces during the water injections are viscous forces, gravity forces, and capillary forces. Capillary forces are the controlling forces in the low permeable reservoir formations, and also they are the dominant forces away from the well, where the viscous forces are lower negligible. But unfortunately, these forces are the most missing forces in the reservoir simulation models. So at this study, we have performed a set of viscous flooding experiment and spontaneous imbibition experiment to study the importance of capillary forces. We have used only a single core to reduce the errors from the pore geometry and also mineralogy of the pores. So instead, we have tried to optimize the restoration method. Each restoration starts with mild cleaning with kerosene and heptane, followed by 1000 ppm sodium chloride. And then we have drying, and then we have initial saturation establishment. And after that, we will have aging for 2 weeks at reservoir temperatures. At the end, we have the main part of the experiment, flooding or imbibition. I have to notice that flooding has performed with the rate of 4 pore volume per day, which is very similar to the real reservoir's flooding rate. And both experiments has performed at reservoir temperature, which is above 130 degrees C. So here at this slide, you see the results from viscous flooding experiments, low salinity injection in secondary and tertiary mode. And what you see is that the low salinity brine significantly improves the displacement efficiency and the oil recovery. And we see that the low salinity brine in tertiary mode is able to improve the recovery. And at the same time that we were monitoring the amount of oil recovered, the pressure drop is also monitored. By looking at the pressure drop, we see that when we move from the modified seawater to the low salinity brine in the tertiary mode, we don't see that much pressure drop. Then it confirms that this improving the recovery is not a mobility ratio effect. And we know that the viscosity of the low salinity brine is almost same as the other brines, high salinity brine. And almost even we can say that it's a little bit less. So of course, it's not a mobility ratio effect. So what's that? To study that, we performed another set of experiments, but using spontaneous imbibition. We have looked at the imbibition of the different brines in the secondary mode and also low salinity brine in the tertiary mode. What you see from the red curve, which is the imbibition, results from imbibition of the formation water, then it confirms that we are in the water wet side. And of course, as the imbibing brine is similar to the initial brine, then it's not the effect of wettability. But when we switch to the low salinity brine in tertiary mode, we can see that the extra oil is recovered. Then, of course, what is this? It's an effect of wettability alteration. When we redo the experiments in the tertiary mode and also in the secondary mode, we see that the low salinity is very efficient, and also the low salinity brine after modified seawater, that's also very efficient. If I summarize the results from my experimental graphically, I can show it in this slide that initially we have oil saturation in a slightly water wet pores. In the pores, we have big pores and small pores. When we float with the high salinity brine, this high salinity brine will go only to the accessible pores with the larger pores and recover some oils. But when we introduce the low salinity brine or the smart water, by changing the wettability, we will actually increase the capillary forces, and that will lead to imbibing of the brine to the smaller pores, which is already bypassed by the high salinity brine. So if I wrap up my presentation, I can summarize it in 3 points. The first, we saw that the secondary low salinity brine injection and spontaneous imbibition of low salinity brine showed significantly increased displacement efficiency. It is most efficient in both speed and also the ultimate recovery compared to the modified seawater and formation water. Increased spontaneous imbibition of the low salinity brine in tertiary mode after formation water or modified seawater imbibition confirmed that the low salinity brine was able to change the core wettability towards more water wet condition as we were expected. And the most important conclusion from my presentation is that the similar oil recovery plateau by both low rate viscous flooding and spontaneous imbibition confirms that spontaneous imbibition due to the positive capillary forces is a major recovery mechanism in heterogeneous pore systems. Thus, it's important to be accounted for in simulation models. At the end, I have to thank the University of Stavanger and the oil company for the financial support and also supporting for the material, and also to the students who helped us. Thank you so much for your listening.
Thank you, Zahra. Very nice presentation. So well done. The next presentation will be held by Skule Strand, also from University of Stavanger. His presentation is titled Effect of Wettability on Ultimate Oil Recovery During Water Flooding. So Skule is Associate Professor in Reservoir Chemistry here at university. He holds a master's degree and a PhD degree in petroleum technology from the University of Stavanger. His main research work is within reservoir chemistry, with a special focus on reservoir wettability and water-based wettability alteration processes for enhanced oil recovery by smart water injection in both sandstone and carbonate reservoirs. So please, Skule, go ahead.
Thank you, Tina. Yes, what we have looked into, Zahra talked now, the previous talk was on capillary forces, and it's a little bit of the same what I'm looking into. And here we have one set of experiments where we are doing smart water EOR processes in carbonates. And what we are doing, in a way, we first, to the figure to the left, we do spontaneous inhibition with formation water, no wettability alteration taking place, and then we switch, in this case, to seawater, which behaves as a smart water in chalk. And what we see when we switch to seawater, we see that we see in the spontaneous inhibition process increased recovery, confirming wettability alteration. And in the same way, for the figure to the right, first spontaneous inhibition, then viscous flooding with formation water, and we come up to a recovery plateau of less than 30%, and then we switch to seawater, and we see a significant increase in recovery by injecting seawater. So, wettability alteration towards more water-wet conditions, that's what we observe, and seawater behaves as a smart water and mobilizes more oil both in spontaneous inhibition and viscous flooding processes. And back to sandstones, the same is what we observe in sandstone. Secondary, to the figure to the left, secondary formation water inhibition come up to a recovery plateau above 30%, confirming quite more water-wet system. And then we switch to a low salinity brine, and we see a change in wettability, confirming wettability alteration. And in the same way, to the right, figure to the right, low salinity injection after formation water significantly improve recovery and gives us so high oil mobilization with formation water, actually both in spontaneous inhibition and viscous flooding, but low salinity still are able to change wettability towards even more water-wet conditions, mobilizing more oil. So, smart water promotes wettability alteration during water injection, and it can significantly increase oil mobilization at more water-wet conditions. So, if we are completely water-wet system, we don't see any smart water EOR effect. What about oil mobilization during water injection at constant wettability, where we don't have a wettability alteration process? So, this is also done experiment done in chalk, spontaneous inhibition with the formation water to secure no wettability alteration taking place, and we see a low recovery in spontaneous inhibition. But when we switch to imbibe and then we switch to viscous flooding on the same core, and we see a recovery plateau up to 30%, close to 30%. So low water wetness give low oil mobilization by viscous forces. Same done on a separate core, where we have exposed it to less crude oil, giving more water-wet conditions. And what we see here, spontaneous inhibition for the more water-wet core. Now we increase the spontaneous inhibition from 13% to 26%, and when we apply viscous forces with formation water, we significantly increase the recovery and have a recovery close to 50%, confirming more water-wet cores give significant higher oil mobilization in viscous flooding processes. And then the third step here, we don't expose the chalk core for crude oil. So we are using a mineral oil. And what's happening here? Spontaneous inhibition are able to mobilize more than almost 75% of the oil. And if we do a viscous flooding in the same core, you see a dramatic higher recovery compared to the less water-wet core systems. So if I plot these recoveries and use Amott water index and calculate that, what we see when I have increasing Amott water index for this core system, we see a significant increase in the oil recovery. So the approach by Morrow don't seem to fit. claiming that we have maximum oil recovery at slightly water-wet conditions. So it's not in line with what we see in smart water IOR process, where we have wettability alteration taking place, and it's not what we see when we are doing experiment at constant wettability. So, oil mobilization from heterogeneous pore system is definitely dependent on viscous forces, could be active, but they will only act at the larger pores. Or in a fractured system, they will only be active in fractures. If you are going to mobilize oil from the smaller pores, you need to induce capillary forces. And capillary drainage of the smaller pores is a major importance in mobilizing the oil. So capillary forces need to be accounted for in models or in simulation tools that we are trying to develop. So that was the main measure of my talk today.
Thank you, Skule, for the presentation. I will remind the people to ask questions in the chat. Please state whom the question is for. So we take a discussion session afterwards when the next presenter has finished. So we have been in the Americas, we have been local here in Stavanger, and now we are moving to a different part of the world, I think. So the next speaker is Maxim Yutkin from KAUST, which is the King Abdullah University of Science and Technology. His talk will be about low salinity or LSW, so low salinity water flooding with dilute seawater is inefficient. That's his claim. And thanks to a classical chemical education, Maxim Yutkin is interested in both practical and experimental research. In his early career, he has dedicated a lot of attention to synthetic coordination chemistry and in particular porous metal organic frameworks. More recently, he investigated the chemistry of fracturing fluids and their interactions with proppant and rock. So please, Maxim, floor is yours.
Good afternoon. My name is Maxim Yutkin. I'm a research scientist at KAUST. Today I'm pleased to present our work on ion exchange-based mechanism of oil recovery. We use the view of crude oil-brine interface presented on the left. There are three parts involved in this picture: crude oil, water or brine, and mineral. Polar asphaltenes and crude oil agglomerate at the oil-brine interface and form microscopic films or skins. An example of such skin is shown on the right. When crude oil receives water during primary drainage, it cannot dry up mineral surfaces completely. At least one or two monolayers of water remain near the surface. The presence of water is important because it cancels weak van der Waals interactions and hydrophobic interactions, allowing only those that can compete with it. At rock roughness valleys, crude oil could not reach mineral surface, and as a consequence, connate water exists as a bulk phase. It connects to the thin films of water at the tips of rock roughness asperities. This way, water or brine remains connected throughout the entire pore network. It is this connectivity that allows injected chemicals weaken the interactions of crude oil with rock roughness tips and produce incremental oil. We can formalize crude oil interaction with rock surface as shown by the first chemical reaction in this slide. The leftmost species represent calcium carbonate surface with deposited crude oil. The greater than sign represents calcium carbonate surface and less than sign represents crude oil interface. In order to detach oil in this particular case, we should introduce a species that will compete with the adsorbed amino group. So here is an example. I use sodium ions, which substitute the amino groups and result in oil detachment. What is important in this reaction is that down to symbol definition and the N coefficient, this reaction can be thought of as an ion exchange process. which is represented by the reaction below. In a more specific case, when n equals 2, we have a classic 2-to-1 ion exchange adsorption isotherm, which can be described in dimensionless form by the last equation in this slide. I would like to highlight this analogy once again. The interaction of positively charged groups at the crude oil brine interface with calcium carbonate surface has similarities to 2-to-1 calcium to sodium ion exchange. Therefore, in order to detach oil, we have to create conditions that disfavor calcium adsorption, which by the analogy will disfavor adsorption of amines and may result in crude oil detachment. There is another mechanism how crude oil can interact with mineral surface, which was discussed in the literature. This mechanism is shown here by the second reaction in the yellow box. According to this mechanism, two negatively charged species, one from rock surface and one from crude oil brine interface, can still interact through a cation bridge, such as calcium ion. If you look carefully and recall the analogy of the first reaction here with calcium to sodium ion exchange, we will see that both adsorption reaction can be reversed by strong cation complexation or by encouraging cation exchange. The same argument applies to the interaction of negatively charged species, of course. Therefore, if we analyze 2-to-1 ion exchange isotherm, we can get an insight on how efficiently design water flood brine composition to enhance oil detachment from mineral surface. In this slide, we look at the behavior of the 2-to-1 ion exchange isotherm at different dilutions. Three cases are considered. First is dilution of seawater with pure deionized water. This means that the ratio of sodium to calcium remains constant, but total salinity decreases. Second case is the dilution of seawater with high concentration sodium chloride brine. That is, sodium to calcium ratio changes, and so does the salinity. Third case is the dilution of seawater with brine of the same chloride concentration and zero calcium concentration. So here chloride concentration is constant and sodium to calcium concentration ratio changes. The graph shows ion exchange isotherms for the three cases. On the x-axis is dimensionless calcium concentration with respect to chloride, and on the y-axis is dimensionless calcium surface concentration with respect to cation exchange capacity. Let's consider first case, the dilution with deionized water, which is shown here by the green dashed line. Arrows indicate salinity decrease direction, and green circle indicates lowest salinity point. We clearly see that in this case, surface calcium concentration increases, which is opposite to what we want. Now let's take a look at the second case, which is represented by the blue dotted line. Arrows indicate the direction of salinity decrease, and the blue circle indicates lowest salinity point. Here we observe that dilution mostly results in an increase of calcium concentration at the surface, except for a narrow region in the upper right corner, where dilution leads to decrease of adsorption. Finally, the last case, the dilution at constant chloride concentration, which is represented by the solid red line. The direction of dilution matches with the decrease of calcium to chloride ratio because chloride is kept constant, that is, salinity decreases from right to left. We see that this case is the only case that consistently and strongly decreases calcium concentration at the surface, and therefore we conclude it is the optimal case. In this slide, we compare results of reactive transport modeling coupled with ion exchange for the following two cases. On the left, it is injection of seawater diluted with deionized water, and on the right, injection of seawater diluted with brine with the same chloride concentration. Let's start with the analysis of the first case, which is shown in the left graph. Abscissa is dimensionless length, therefore we look at the concentration profiles. The left ordinate is bulk ion concentration and the right ordinate is dimensionless surface concentration with respect to cation exchange capacity. Only half of pore volume was injected, so concentrations to the right of 0.5 dimensionless lengths are those initially present in the column, and the concentrations to the left of 0.5 dimensionless lengths are injected ones. The spread between the zones is due to dispersion. Before we start the analysis, I would like to remind that the goal of this treatment is to reduce adsorbed calcium at the surface, which is represented by the blue dashed line. First, we see classic tracer breakthrough curve represented by chloride ion. Bulk ion concentrations decrease proportionally, each by a factor of 2. This is the dilution. If we compare values that the blue dashed line attains before and after 0.5 dimensionless lengths, we will see that injection of diluted seawater increases calcium absorption as predicted by the adsorption isotherm. Therefore, such treatment is inefficient and unfavorable. The graph on the right features the optimal dilution modeling result with the same initial input parameters. The dilution corresponds to the third case considered above, namely to constant chloride concentration case. Indeed, as we can see, chloride concentrations remains unchanged when it passes through the point of 0.5 dimensionless lengths. Sodium concentration increases while calcium concentration decreases. More importantly, we now see a decrease in adsorbed calcium concentration, again as predicted by the ion exchange adsorption isotherm. We conclude that such dilution approach can favorably affect oil detachment. I would like to conclude by showing some experimental data from Emmett's spontaneous imbibition test where some incremental oil was recovered using the approach represented. When we follow guidelines from the ion exchange isotherms and use brines that encourage calcium desorption, we reproducibly observe a few percent of incremental recovery. In this regard, the information on the efficiency of the exchange by the ion type could help increase the recovery margins. In contrast, when we follow the simple path of dilution with DI water, we never observe incremental recovery. In the end, I would like to acknowledge the conference organizers, our sponsors, my colleagues, and of course you for your kind attention. I will be happy to answer your questions. Thank you.
Hello, my name is Alexander, and I'm going to finalize this part of the first session by asking the questions which we got during the presentations. And first of all, I would like to thank all the presenters for interesting presentations. And we got a few questions. So the Q&A session will be going in a way that first I will be asking questions for people who are present here in studio, and then I will try to address the questions to people online, and if we have possibility to get an answer from online, that would be great. And first we will start with Skule Strand. So he's standing in front of me. And Skule, thanks for a very nice presentation, very interesting. And you get a couple of questions. The first question. So it is clear that both in sandstone and carbonates, there is a change in rock wettability. So it was clear from your presentation. However, the time scales of response for viscous flooding in terms of oil mobilization for both rocks are different. So that is for carbonate rocks, you show a quicker response compared to sandstone experiments. So do you have an explanation for that? So in terms of oil mobilization and the time response for that?
There is always answers to any questions, but generally the understanding of carbonates versus sandstones, what we see from experimental data is that the response on the wettability alterations response is much faster in sandstones compared to carbonates. If you do a core imbibition experiment on a single core, definitely we see that we reach the recovery plateau much faster generally in sandstone compared to carbonates, and it's linked to the mechanism behind the wettability alteration process. So in sandstones there is a pH change that dominates the recovery or the wettability alteration process, and pH are protons. And proton reactions are fast reactions. So as soon as you have a wettability alteration, with proton depending on proton interaction, it's a fast process. In carbonates, the wettability alteration in carbonates, what we have tried to explain is that it's a combined interaction between sulfate and calcium that are needed for desorbing negatively charged polar organic components that are desorbed on the mineral surface. And so it's a slower process because we always need to have enough sulfate available in the injection front. So.
Yes, thank you, Skule, for a very detailed answer. So we have another question to you. In your presentation, you stated that did not match the morose recovery versus wetting plots, and then that capillary pressure must be included in simulations of the data. Do you mean that you would match by including capillary pressure, or that morose plots did not include capillary pressure, and therefore simulation is required to get correct recovery plots? So do you have any comments regarding that?
I have looked into the Jahardran, the PhD thesis of Jahardran, and it's quite clear that they are comparing spontaneous emission with observations on recovery processes, and I think how to include capillary forces in oil recovery processes, I think that's the key. How to do it, and if it can be done with the capillary pressure, or if it can be only done with simple spontaneous emission experiments. I think if I would start doing the modeling work, I would have based it on spontaneous emission experiments, and skip the capillary pressure approach. Because the process of measuring capillary pressure is, in a way, is nothing that will happen in your reservoir. In the reservoir, we hardly have a pressure drop. And working with 5 bars in pressure drop over a core when we are producing the capillary pressure curves, for me it seems to be a little bit... it's not the physical process that are taking place in the reservoir. Yeah.
Yes. Thank you, Skule. I feel myself like I'm on a PhD defense, but instead of you asking question, then I'm asking question to you this time. And yeah, so thank you very much for answers. And then I would like to ask Zahra to come and join the questioning. And Zahra, thank you for the presentation. And we got a few questions to you as well. So the first question is that first question is, how does the kerosene affect the core wettability during cleaning procedure? So what do you think about that?
Yes. Okay. We believe that actually in the normal way of the cleaning that has done performed in most of the research centers, it's cleaning with toluene and methanol. And that's a harsh cleaning, so it will remove all the active polar components which is already adsorbed to the surface. And this will end with the core very much waterbed. So we believe that by using kerosene instead of toluene, we are trying actually to keep the initial wettability as it is in the reservoir. Yeah. Yes.
Thank you. Thank you very much for the answer. And another question. Which kind of clays do you have in the core you have used, and how do you think the swelling tendency of certain clays, if it happens, will affect your results? And do you think that you're altering those clays, enhance the mineralogy while cleaning the core several times, or not?
Yes, our course has containing about 8% of the different kind of the clays, mostly kaolinite and elite. And also, in addition, the core has about 15% of the feldspar, which has positive effects during the smart water smart water injection. So the the clay content is high enough to see the mechanism, to see the effect. And the next question, which was about swelling, actually we believe that these clays, both kaolinite and elite, they are not swelling clays, so we don't worry about it. And also during the cleaning procedure, what we see is that no change in mineralogy happens. We don't see any clays in the outlets, and also the core weight is always similar to the previous restoration. So that confirms that we don't have any losing of the minerals during the cleaning and restoration procedures.
Thank you, Zahra. And then there is a last follow-up question, which came up right now. So when using kerosene, do you consider asphaltene stability and whether wetting might be altered due to crude kerosene asphaltene incompatibility?
Actually, prior to each experiment, we measure the asphaltene content, and we have the centrifuge to remove the heavy components. So we expect that we don't see any asphaltene precipitation during the procedure. And as we know, the asphaltene precipitation is most likely it's dependent on the pressure. And so we believe that we don't have any asphaltene precipitation during the experiment.
Yes, thank you very much, Zahra. Okay. So if it's okay, we can move forward with the presenters which are not present right now in the studio. And we have a couple of questions to Patrick Brady. So if Patrick, you can unmute your microphone if it's possible and reply to those questions, it will be great. So please just let me know if it's possible. And we also have...
Sure.
Yes, Patrick, hello? Can you hear me? Yeah, Patrick wrote in the chat that there is some...
I don't know if you can hear me, Alexander, but
we can hear you well. Can you hear us?
No, I cannot hear you, Alexander. The connection is gone bad.
Okay. That wasn't a good idea. Yeah, so Patrick, if you can hear us, so I can probably ask a question. So the question was that the question was if you also studied the effect of brine.
The connection is not good. Go to someone.
Okay, okay. So maybe we can have Maxim Yutkin online.
Yes, hello. Can you hear me well?
Yes, we can hear you well. Can you hear me?
Yes, I can hear you. Let me turn on my video.
Yes.
And I guess that works. So yes, here.
Okay.
So,
I don't know, Maxim, if you checked the question in the Zoom.
Let me see. I have checked questions. There is only one question.
Yeah, there was a question addressed to you from the person Omid. Yeah.
Yes. So, well, I wanted to type in the answer, but I didn't quite get the question, so that's why I didn't. So, is there any chance, I mean, you can very quickly clarify it in the chat? So the question is: have you also thought how to
take probably, yeah, with the rest of
calcium
in terms of yeah,
calcite cement formation? Well, I just don't understand why we need to kind of consider calcite cement formation. In general, so the simulations that I showed, they were all basically in equilibrium with calcite. So whatever was injected, whatever processes happened during the simulations, they were the modeling software forced equilibrium with calcium carbonate. Whether there was some dissolved or precipitated, I cannot I just answer right off the top of my head. But of course, there was some dissolution and precipitation. Yeah, yes. Yeah, that's what I can say. And during this process, it can happen. It really depends on the conditions that you use. It depends a lot, for example, on CO2 in reservoir and how much CO2 you input in your calculations.
Thank you, Maxim. Maybe you can also comment on the question which was not addressed to anyone. I guess it's just a question for all presenters. So the question was, what's the ambiguous aspects of smart water injection and the effectiveness of wettability alteration? Do you have any comments on that?
Let me scroll to the question.
Yeah, the question was from Saeed.
Is it in the answered questions or?
It's in question and answers chat.
Ambiguous aspects. Well, I mean, the entire field, in my opinion, is a little bit ambiguous because, well, we all seem to agree that wettability alternation is necessary, right? And this is how the recovery happens. We all seem to agree that to see the effect of smart water or low salinity water flooding, however you call it, asphaltenic crude oil with partially or mixed wet, let's say core plugs or oil reservoir is needed. Otherwise, we don't see these effects. But apart from that, we do not seem to agree on many other things. For example, how does that wettability alternation happen? For example, Stefan asked another question in this chat. If we can explain the wettability or the recovery not by liquid-solid interaction or not by liquid-solid process, but only using the liquid-liquid processes, for example, using interfacial rheology settings, right? For the talk that I presented basically says that, the dilute seawater is inefficient. Well, if you look at it from a very simple perspective of ion exchange, is inefficient in undoing the ion exchange based interactions of crude oil with minerals, right? While other results may suggest otherwise, actually, right? And they were presented. So this is these are the ambiguities, and I barely scratched the surface, basically.
Well, thank you, Maxim. I guess Skule has a couple of comments.
More linked to this IFT or liquid-liquid process on smart water, and we have tried to measure IFT for the systems that we have been working with, and we don't see significantly changes in IFT, the interfacial tension between the oil phase and the brine phase that we are using. So there is a slightly decline in increase in IFT if we are lowering the salinity of the brine. But that's a general understanding of IFT. So if I'm working with distilled water, I have a higher IFT compared to if I add a little bit of impurities into the distilled water system. But it's no significant changes in IFT that can explain this huge change in recoveries that we observe.
Skule, while you're here, we have another question. We still have 5 minutes before the break. So do you see contact angle as a good factor to evaluate wettability alteration while injecting smart water? What do you think about that? Contact
angles is, in a way, it's a theoretical approach or a fundamental approach trying to understand wettability on homogeneous surfaces. And if there is something that we do not have in reservoirs is homogeneity. We have heterogeneous pores, we have heterogeneous mineral distribution within the pore surfaces, and so I have a problem understanding the approach of trying to apply contact angle measurements. And if you think about that, the wettability is partly dependent on the amount of oil we expose the mineral surface to. If I'm working with a small mineral surface that I try to apply a oil droplet on and try to measure it, so then we have a huge amount of oil compared to the square meter of surfaces available. So I'm skeptic to that. I think it's spontaneous emission is very simple. It's something that everyone can do in a lab and measure the wettability of your restored core.
Yeah, thank you. And probably the last question. Do you have any methods to examine pure minerals for smart water? I guess if we work with the sandstones, for example, can we examine the smart water effects for specific minerals?
We have looked into the chemical reactivity of the individual minerals that are present in sandstones. And it's not only quartz. So there are clays, and we have discussed clays previously, and clay minerals seems to be the important wetting mineral. But there are also feldspars that for sandstones that are very important for the change in pH that facilitate the wettability alteration process. So feldspars are basic minerals. So when you introduce a low salinity brine, they interact with your brine system and take up cation ion exchanges on feldspar minerals, take up protons. No, yeah, take up protons from the water and increase the pH of your brine. So yeah, that's I think that's my answer to that.
Thank you, Skule. I think we will finish with the questions and answer for the first part of the first session. I will kindly ask you to ask questions as much as possible during the presentation, because for me personally it's a little bit difficult to keep the conversation and also check which questions are appearing online. So try to think of question and write it down during the presentation time before questions and answer session, so I can prepare it and ask the presenter. Otherwise, thank you everyone for presentation, and we have a little bit more than 10 minutes break, and we start the second part of the first session at 2:15. Thank you.
Hello, welcome to the second session of Fundamentals. So the next speaker is Maria Bonto from DTU, and her title is Measurements of Kinetics Properties of Indiana Limestone with two different methods. Maria Bonto studied a double degree in chemical engineering and energy engineering at Rey Juan Carlos University in Madrid, Spain. Her research interest during that stage was related mainly to the design of thermal and thermochemical storage of concentrated solar power plants. Afterward, she continued with a Master of Science in Petroleum Engineering at the DTU, Denmark, and she is currently pursuing PhD studies at the same university. Okay. Maria.
Hi, my name is Maria and I'm a PhD student at DTU. Today I will present some work that we did during my 3-month external stay at KAUST. There we measured and compared the zeta potential of Indiana limestone at high ionic strength through streaming potential and electrophoresis. I will start with a brief introduction to the source of the electrokinetic phenomena. In presence of water, mineral surfaces become charged, and this charge leads to the development of an electric double layer. As shown in the figure at the left, the electric double layer consists of a compact layer of ions known as the Stern layer and a diffuse layer with mobile ions. The thickness of the diffuse layer is usually estimated through the Debye length. The excess charge at the surface leads to an electrical potential with respect to the bulk. Experimentally, what is determined is the potential at the slip plane, which represents the boundary between stagnant and mobile ions. The electrokinetic potential has important implications for transport in porous media, giving an indirect measure of adsorption and being related to the wettability. Although measurements at low ionic strength are readily available, subsurface environments are characterized by higher salinity. At high salinity, the theory suggests that the double layer collapses. This behavior is displayed in the outer figure at the right that shows the abrupt decrease of the Debye length thickness with salinity, and the inner figure shows the fall in the potential with distance for different salinities. This suggests that at high electrolyte concentration, all the excess charge is located in the Stern layer and the zeta potential should be zero. However, streaming potential measurements have been reported that show a non-zero zeta potential at high salinity. To validate this, we decided to compare the zeta potential of Indiana limestone obtained from streaming potential to the well-known electrophoresis method. I will now explain what is the streaming potential and how we measured it. So let's say we have a core saturated with brine. When flow is imposed, the ions in the diffuse layer are dragged, leading to a streaming current and therefore to a streaming potential. At the same time, the streaming potential causes a conduction current in the opposite direction. The streaming potential coupling coefficient is then determined from the ratio of the potential difference and the pressure drop at steady state, when the conduction current is equivalent to the streaming current. A schematic of the experimental system is shown at the left, and on the right I've included a picture of the real setup. There are two tanks, one at each side, both containing oil and brine. A syringe pump supplies the oil, which pushes the brine through the rock sample contained in the core holder. With this design, flow can be induced from either side, and this allowed us to perform paired experiments. The oil does not serve only as hydraulic fluid, but also insulates the system, ensuring that there is no flow of electrical current along the brine, and that the measured potential difference comes only from the rock sample. During the flow, pressure transducers allow measuring and monitoring pressure drop across the sample, and the induced streaming potential is measured through silver chloride reference electrodes that are connected to a multimeter. Before inserting the sample in the core holder, we wrapped it in a rubber sleeve, and at each side of the core we placed plastic end caps with conductor wires in contact with a thin metallic mesh attached on the surface of the end cap. This allowed us to measure the sample resistance and infer the conductivity of the saturated core at its salinity. A picture of these end caps is shown at the right next to the experimental setup. The streaming potential measurements rely heavily on the electrode's performance. We initially started with the two types of electrodes shown on the slide at the left. These were designed by a manufacturer, but we could not obtain any measurements either because they were very unstable or had a very high offset potential. Then we decided to make our own electrodes, which are shown at the right, by depositing silver chloride on a silver wire. This was a very long process where we tried many different options, not only for the silver chloride deposition, but also for the design of the reservoir that encapsulates the electrodes and porous membrane at the bottom. We finally coated the silver wires by submerging them in hydrochloric acid and applying a low current density for 12 hours. After the electrodeposition, we aged them for at least 24 hours in a high concentration potassium chloride solution. To avoid the dissolution of the silver chloride layer, we added some precipitated silver chloride to the potassium chloride solution to ensure its saturation. This improved the stability of the electrodes. Finally, to regenerate the electrodes, we soaked them in dilute ammonia. We spent significant time on the electrodes fabrication because their stability plays a major role in the success of the experiments. The figure on the left shows the evolution with time of the flow rate, pressure drop, and potential difference during an experiment. As observed, increasing the flow rate leads to an increase in the pressure drop and consequently of the streaming potential. Steady state is achieved when both pressure drop and potential difference maintain constant. We record the stabilized values when flowing from left to right, and then we reverse the flow and obtain an opposite pressure drop and streaming potential. From the stabilized streaming potential and pressure drop, recorded when flowing from both sides, we obtain average values. The ratio of the average streaming potential and pressure drop gives the streaming potential coupling coefficient. This paired procedure of carrying out the experiments minimizes the electropolarization effects and also eliminates the electrode's offset potential or its change during the experiment. The case shown on this slide is a fairly satisfactory one, although some drift in the potential can be observed at constant pressure drop. However, when the electrodes perform poorly, it is not uncommon to record only noise or to observe that, although the pressure is constant, the potential does not reach a steady value. The two figures at the bottom left show the linear increase of the streaming potential with the pressure drop at two different potassium chloride concentrations. The slope of these graphs corresponds to the streaming potential coupling coefficient. For each case, we used 3 or 4 flow rates and we repeated the test to determine the experimental uncertainty. To convert the coupling coefficient to zeta potential, we used the modified version of Helmholtz-Molokowski equation that includes the formation factor. We determined the formation factor by representing the rock saturated conductivity against the fluid conductivity as shown in the bottom figure at the right. For the electrophoretic mobility measurements, we prepared the solutions and then with a mortar and pestle, we crushed the Indiana limestone sample. We equilibrated the solutions with the rock powder for several days at atmospheric CO2 and room temperature until it reached a stable pH value consistent with the equilibrium pH predicted by frequency. For the measurements, we took samples from the middle of the suspension and we prepared several dilutions so that to find the particle concentration range that results in constant electrophoretic mobility. The solid concentration of a suspension was determined with a spectrophotometer, and then we proceeded to measure the electrophoretic mobility and the particle size distribution. This methodology ensures suitable particle size and concentrations in the suspension that minimizes settling and also secures saturation conditions with respect to calcite. According to the characteristics of our system, the zeta potential was inferred from the electrophoretic mobility through Molokowski's equation. This figure shows the potassium chloride concentration on the x-axis and the zeta potential on the y-axis. The blue triangles and the black circles correspond to the zeta potential of Indiana limestone from streaming potential and electrophoretic mobility respectively. For comparison purposes, we have also included, shown as red squares, the zeta potential of pure calcite measured through electrophoresis. At low ionic strength, the zeta potential estimated through the two methods are consistent. However, a great discrepancy is observed at 0.5 molar. At that salinity, the zeta potential of Indiana limestone from electrophoretic mobility shows a magnitude similar to that of synthetic calcite. Although given the short time of the project, we did not have the time to dig into the cause of these discrepancies, several aspects may be behind these differences. First, grading the samples for electrophoretic mobility may result in additional freshly created surface size compared to streaming potential. And second, the equilibration procedure is different in the two methods, as the closed setup of the streaming potential hampers the equilibration with the CO2 phase. Since sample preparation methods and equilibration procedure can strongly affect the measurements, we recommend close monitoring of the solution, not only by conductivity and pH measurements, but preferably also by characterizing the chemical composition of the effluent through ion chromatography. To conclude, we could not validate the streaming potential measurements at high salinity by comparison with the electrophoretic mobility measurements. We postulated that this kind of validation cannot be carried out because the sample preparation for electrophoretic mobility measurements requires grinding of the rock, which will expose fresh surface ice that are not exposed in the streaming potential measurements. This also means that the streaming potential measurements at high salinity remain unvalidated, as nobody has been able to validate them yet. Regarding the streaming potential experiments, besides emphasizing that the electrodes design is crucial for successful and stable measurements, we were surprised to see that papers reporting this type of tests do not provide a thorough description of the electrodes fabrication, nor provide the name of commercial suppliers of such electrodes. To finalize, I would like to thank all those that have made this work possible and have guided and supported me throughout my external stay.
Thank you, Maria, for a nice presentation. The next speaker is Mikhail Levant. And the title of the presentation is Surface Probing with Streaming Potential, the Polymer Flooding Scenario. And Mikhail Levant works as a laboratory manager, leading a team of 2 to 5 persons, co-supervising PhD students and postdocs as part of the joint research laboratory between Total and ESPCE in Paris. His activities include upstream research or physical chemistry of dispersions in confined flows, and his interests are within produced water reinjection, low salinity, water flooding, water treatment, sustainable energy, experimental fluid dynamics, milli and microfluidics, electrokinetics, and additive manufacturing. So,
hello everyone. My name is Mikhail Levant. I'm a research engineer in the R&D center of Total, the global energy company, located in the southwest of France. The work I'm about to present to you today was done as part of a postdoc project in the joint research group with ESPCI in Paris, one of top French engineering schools. What we did here was, for the first time, to use the streaming potential as a method for surface probing inside an intact core at high salinity to detect the impact of polymer flooding, which is not typically used for streaming potential. And I also invite you to check our paper in Transport and Porous Media for more details. I will start with some basics. The streaming potential is closely linked to the zeta potential and stems from local non-zero concentration of charges close to a charged interface, in a region we refer to as the diffuse layer. Now, when a charged interface comes in contact with an electrolyte, the counter charges tend to screen the surface charge, so they arrange themselves in such a way that the surface potential goes to zero as we go farther away from the interface, together with the charge density, as you can see on the left. This structure is commonly presented as a model of 2 layers, separated by a slip lane, which separates immobile charges that are closer to the interface from mobile ones in the diffuse layer. Commonly, the potential in the vicinity of the slip lane is where we define the zeta potential. And obviously, for more saline electrolyte, the potential decays faster and the zeta potential will be lower. The takeaway message from this slide is that the excess charges in the region of the electrolyte that we call the diffuse layer are mobile. Now, since the diffuse layer charges are mobile, it means that we can displace them. For example, by applying an external pressure gradient, which in fact generates a current. Now, under proper measurement conditions, this current can be read as potential difference across the sample, also known as the streaming potential. The faster the flow or the higher the pressure gradient that we apply, the higher will be the measured voltage. And the sign of the measured voltage, or more accurately, the sign of the voltage response to the applied pressure gradient, will depend on the sign of the displaced charges. In fact, when certain experimental conditions are satisfied, the streaming potential is proportional to the applied pressure gradient via the streaming potential coupling coefficient, which is in turn proportional to the zeta potential, but can also provide lots of information on the state of the surface by its own, as we are about to see. Now, in this example, the coupling coefficient is positive, and since all the additional parameters in the Helmholtz-Smoluchowski equation that you can see here are also positive, the zeta potential has the same sign. The sign is obviously determined by the counter charges and therefore can serve as an indicator of the sign of the surface charge. In our experiments, we are using a hydraulic circuit that enables fluid flow through the sample and a simultaneous measurement of the streaming potential in both directions of the flow. This was done to avoid polarization, and we also have a system of valves that enables injection steps. The sample that we were using is a cylindrical carbonate core from the Estayat quarry in France. Our experimental scheme is the following. So we start with saturating the core with synthetic formation brine, which has ionic strength of about 3 mol per liter and is rich in calcium, magnesium, and carbonate ions. In these conditions, the coupling coefficient is positive. Next, we inject a polymer solution, which is a highly concentrated solution of hydrolyzed polyacrylamide in formation brine. So hydrolyzed polyacrylamide is commonly used in enhanced oil recovery. The polymers in the solution and the rock surface are oppositely charged, which we assume to be a favorable condition for adsorption. To test whether this is true, we continued to the next step, which was chase flooding. So we flooded the core with formation brine to remove any non-retained polymers, and while doing so, we monitor the pressure drop across the core as well as the viscosity of the effluents to make sure that all the non-retained polymers have left the core. After the chase flooding, the core is back to be saturated with formation brine, except now we expect the surface to be modified by the adsorbed polymer. The chase flooding step was there to assure that the final measurements are not impacted by the content of the aqueous phase. And indeed, when we repeat our measurements of the streaming potential coupling coefficient, we see right away, just from the raw data, that the surface is now negatively charged. So the blue and the red points on the plot on the right correspond to the coupling coefficient before and after the polymer flooding, respectively. What is also interesting is that we obtain similar results, whatever was the molecular weight of the hydrolyzed polyacrylamide that we used when we followed the same scheme. So we had positive sign before the polymer flooding at bare rock surface and negative sign after chase flooding when polymers were adsorbed to the surface. So to conclude, we presented the method for direct surface probing inside intact cores that performs well at high salinity with high signal-to-noise ratio, particularly in application to polymer flooding. We also presented the first experimental evidence of polymer adsorption in carbonate cores obtained with this method. Finally, if sign inversion is indeed linked to wettability, as we say it is, it needs to be considered when performing polymer flooding. And now I wish to thank my co-authors and my colleagues that took part in this project, and I would like to thank you for your attention.
Thank you, Michael, for a nice presentation. The next presenter is Hassan Mahani from Sharif University, and the title of the presentation is Pore-scale observation of brine-chemistry dependent oil recovery using a calcite microfluidic ship. Hassan Mahani has over 15 years of experience in both industry and academia. He holds a PhD degree in petroleum engineering from Imperial College and a Master of Science degree in chemical engineering from Sharif University and Technology. He currently serves as an associated editor for SPE Reservoir Evaluation and Engineering Journal and Journal of Petroleum Science and Engineering. His research is geared toward fundamental understanding and quantitative evaluation, modeling and prediction of multiphase flow in porous media with applications to IOR and EOR, geoengineering and environment. Okay.
Hello and thank you for watching this video. This presentation is about pore-scale observation of brine-chemistry dependent oil recovery using a calcite microfluidic chip. This study is about low salinity or controlled salinity water flooding, which is a means to improve oil recovery from reservoirs. Low salinity water flooding efficiency is governed by oil, brine, and rock characteristics and their binary and ternary interactions. These interactions define the initial wettability state of a system and also the pore-scale events during the displacement. In this study, the main focus is on brine chemistry and how it influences the oil recovery by this method. This study is at pore network scale, and for that purpose we have fabricated a double-sided calcite micromodel using the lithography method. The procedure has been shown on the left-hand side, and you can go through it in your own time. This procedure involves using a calcite crystal, and the pore network pattern is etched on the calcite using a photoresist, a photomask, and acid wash. On the right hand side, the manufactured micromodel of REV size has been shown, which is 2 cm wide and 4 cm long. This is showing an unsaturated micromodel. The physical characteristics of this micromodel has been shown in this table. In the microfluidics experiments, a number of brine were used, which includes high salinity formation water, diluted seawater, and modified seawater with calcium, with sulfate, and with silica nanoparticles. We have also used reservoir crude oil with the properties shown in this table. All the flooding tests were performed in tertiary mode, which means that we initially flooded the system with high salinity formation water, and thereafter we injected each of the low salinity or modified brines. To make sure that the recovery is not influenced by the viscous forces or the injection rate, we have used a multi-rate injection procedure. And to allow for the time effects, particularly during the low salinity water flood, we have also included a shutting period of up to 15 days, which means that we have allowed spontaneous inhibition in the process. To better understand the underlying mechanism, we also performed contact angle measurements using a modified method. We have also measured the oil brine IFT with each of the brines. In this slide, you see the contact angle results using the modified method, which includes dynamic salinity alteration. In this modified method, which has been already published in our previous papers, we allow the oil droplets to reach equilibrium with formation water, and then after equilibrium with formation water, we exchange a brine with the target or the brine of interest. Here you see the contact angle results in formation water, and after switching to each of the brines, seawater and diluted seawaters. Here you see that among the diluted brines, 10 times diluted seawater is the most effective brine in changing the contact angle from 91 degrees to 53 degrees. In this slide, you see the contact angle results using the same method with each of the modified brines, which includes modified seawater with sulfate, with calcium, and with silica nanoparticles. And as you can see from this contact angle profile versus time, the largest changes in contact angle are observed with seawater augmented with silica nanoparticles. So this brine is the most effective brine towards change of wettability. Here we see the flooding results with 10 times diluted seawater and seawater augmented with silica nanoparticles after injection of formation water. The top images show the remaining oil saturation and distribution after formation water flooding in the whole micro model, and the two bottom images show the oil distribution after flooding with each of the brines. The middle images show the oil distribution during the injection with each of the brines, and we interestingly note that during the injection of a large volume of 10 times diluted seawater or seawater with silica nanoparticles, there is no change in the oil distribution. However, after allowing a sufficient amount of time during the shutting period, we note that a significant amount of oil is recovered, which means that spontaneous imbibition is really necessary to recover oil in the system after the initial flooding. With silica augmented seawater, we reach the ultimate recovery of 91%, and with 10 times diluted seawater, we reach the ultimate recovery of 80.5%. Similar to the previous slide, here we see the results of flooding the micromodels with modified seawater with two important PDIs like calcium and sulfate. Similarly, the top images show the oil distribution after flooding with formation water, and the two bottom images show after injection of the modified seawater. As you can see, similar to the previous case, these two modified brines also have improved the sweep efficiency and ultimate recovery. However, these two brines were not found as effective as diluted seawater or modified seawater with silica nanoparticles. The ultimate recovery reaches 73% with SW with 2 times sulfate concentration, and the ultimate recovery with seawater with 2 times calcium concentration reaches 66%. In this slide, we look at the incremental recovery factor as estimated from image analysis versus the contact angle change as obtained from contact angle measurements. As you can see, there is a monotonic relationship between the two, and the highest changes in the contact angle results in the highest oil recovery factors. So we can use the contact angle measurements to predict the performance of each of the brines at the pore network scale. However, validity of this prediction for the core scale and beyond requires further tests. The main conclusions of this study are as follows. We have successfully manufactured and demonstrated the usage of a double-sided calcite micromodel using lithography method. We have observed significant improvement of microscopic sweep by diluted seawater and modified brines under tertiary mode. The mechanism of oil production involves formation of microscopic devetting patterns coalescence of these patterns, and thereafter oil removal from the surface. We found that contact angle results were predictive of the expected oil recovery at the pore network scale. We also observed that the recovery process is quite slow with all of the brines, which takes at least 5 to 12 days to reach the final recovery. We also note that viscose flow of modified brines is not sufficient to recover the oil. Spontaneous imbibition of brine following the reduction of contact angle or capillary pressure is key to recover the remaining oil. Thank you for watching this video, and I would be more than happy to take your questions during the symposium. Thank you.
Thank you, Hassan, for your presentation. Just a reminder to the audience, if you want to question any of the presenters, please use the Q&A chat. Okay, the next presenter is Muataz Abu-Al-Saud from Saudi Aramco, and the title of the presentation is Predicting of Smart Water Synergy with IOR in Carbonates Using Surface Complexation Modeling. Muataz joined Saudi Aramco in 2009 and is currently working as a research engineer in the XPEC Advanced Research Center in Reservoir Engineering Smart Water Flood team. He received his bachelor degree in mechanical engineering and mathematics from Rice University in Houston. He earned a master's degree in mechanical engineering from King Abdullah University of Science and Technology in Saudi Arabia, and a PhD in energy resources engineering from Stanford University in 2017. His research interest is focused on fundamental understanding of multiphase flow inside carbonates from the nanoscale to the reservoir scale, as well as digital rock physics. Okay.
Good afternoon, everyone. My name is Muataz Abu-Saud, and in this talk I'll present to you prediction of smart water synergy with IOR and carbonates using surface complexation modeling. My colleagues and collaborators are Aman Al-Ghamdi, Subhash Ayrala, and Abdul Karim Al-Soufi in Saudi Aramco. Here is briefly the outline of the talk. First, I will talk about the motivation and challenges. Then I will give a brief background about the electrokinetic interactions in carbonates. Then I briefly show some of the electrokinetic results of modeling and experiments. Then conclusions are presented together with path forward recommendations for future work. Water flooding is one of the most successful and widely used methods in oil recovery for both carbonate and sandstone formations. Yet, the physiochemical interactions associated with water injection process for oil recovery are not fully understood, especially for carbonates. In oil recovery process, there are complex interaction of forces such as gravity, viscous, reactive, and capillary forces. Such forces occur at the micro scale, the pore scale, and also the atomic scale, and impact the fluid flow at the reservoir scale. Typical microscopic multi-phase Darcy model does not provide fundamental insights on fluid flow in oil recovery process. That is why we need to study the physiochemical interactions at the micro scale to be able to optimize smart water with and without IOR processes and be able to maximize the oil recovery from reservoirs. Numerous studies have shown that surface electric charge manipulation is the main driving mechanism behind wettability alteration observed in controlled ionic composition water flooding processes in carbonates. Interaction of surface charges at the atomic scale dictate the carbonate reservoir wettability. For instance, if the water salinity results in opposite charge polarity of brine, calcite, and brine oil interfaces, the wetting state is unfavorable as shown in the left side, more oil wet. However, if the water ionic composition is controlled to result in negative charges of both interfaces, the wetting state is favorable and more water wet in carbonates. Here we are interested to evaluate and understand the electrokinetics of different brine recipes, including chemicals, to study wettability alteration in carbonates based on zeta potential measurements and predictions using surface complexation modeling. Surface complexation model is used to predict the adsorption of ions based on specified surface reactions at equilibrium state. For instance, the dissolved ions in brine get partially adsorbed on each interface, calcite and crude oil in this example. The adsorbed ions dictate the surface electric charge of each interface based on their concentration, charge magnitude, and charge polarity. The determined surface electric charge corresponds to a zeta potential parameter for each calcite brine and crude oil brine interfaces. Here we elaborate on the surface reactions associated with the calcite surface. In this work, we use surface complexation model with surface reactions similar to the approach of Song et al. To predict zeta potentials for pure calcite and different brine recipes. To elaborate, the hydrated calcium components serve as the calcite sites that interact with the hydrogen ions to create a surface complex according to this equation governed by a specified reaction constant with a specific value. Similar reactions occur for the rest of the ions that also interact with the hydrated carbonate component of calcite surface according to the shown surface reactions in this slide. The number of moles of each adsorbed surface complex ion determines the surface charge and the corresponding zeta potential. As for the crude oil surface, we determine brine crude oil zeta potentials by modeling SCM reactions at the brine crude oil interface using a similar model presented in the work of Takia et al. Illustrated in the figure on the right, and also similar to the work of Bonto et al. And Brady et al. In these surface reactions. So the carboxylate group and nitrogen-based groups interact with the individual brine ions according to the shown surface reactions and corresponding reactions constants. Now we will show some of the experimental results and SCM modeling zeta potential based on these equations, which are for the calcite, pure calcite, and crude oil surface. First, we show the SCM results for the calcite brine oil without any chemical IOR as a baseline. The value of the equilibrium constant shown in the previous slides for the calcite brine and brine oil has been adjusted to minimize the discrepancy between the experimental and SCM zeta potentials. The SCM modeling results capture the trend observed in the experimental zeta potential measurements, developed using Frick-C geochemical modeling software. The zeta potentials strongly depend on the divalent ions, calcium, magnesium, and sulfate, where the sodium sulfate recipe shows the most negative zeta potentials, while the high salinity recipe has the most positive zeta potentials due to the high concentration of hardness ions, the calcium and magnesium. For crude oil brine interface cases, which is shown in the right figure, the SCM zeta potentials results qualitatively matched the experimental observations. The predicted zeta potentials are in general negatively charged as shown in the right figure, which is consistent with the experimental results. Also, the intrinsic equilibrium constant are in agreement with the literature. The values are in the just recently published manuscript that we have. Now we add chemical surfactant, which is anionic at 0.1% weight, which is 1000 ppm. In this case, we add anionic surfactant, which is negatively charged. The addition of anionic surfactant pushes the zeta potential values towards more negative for all brine recipes compared with the baseline case and illustrated in the above figures. Similar effect has been observed when another type of anionic surfactant we have experimented with that differ in terms of the carbon number chain length added to the brine recipes. The The negative trend of zeta potential is due to anionic surfactant molecules adsorbed on top of the divalent cations that has been modeled in the SCM, especially for high salinity case. We also have additional results that include different surfactant such as amphitoric surfactant and non-ionic surfactant. We have also experimented with CO2 dissolved at high pressure without chemicals, but as a IOR process. But due to the time constraint, we just show the results of anionic surfactant results, and this is just the beginning of research that we have in Saudi Aramco. So in conclusion, this work evaluates the synergy of different surfactant types and brines to study wettability alteration based on zeta potentials through surface complexation modeling and experiments. Water chemistry is crucial to optimize IOR performance and improve oil recovery through wettability and bulk property enhancement. Here we showed anionic surfactant synergizes well with the considered brine recipes through pushing the zeta potentials towards more negative. Additional experimental data is required for further validation of the SCM model, including adsorption data for more robust zeta potential predictions. This is an ongoing research in Aramco, and further refinement and details will be considered for both experimental and modeling. I would like to thank and acknowledge Hussein Salim, Mohammed Utaybi, and Dong Q Cha for their help with the zeta potential measurements. Here are some of the references, and I will be happy to answer your questions. Thank you for listening.
Yes, we are back to studio, and thank you very much all presenters. It was very interesting presentations, and we have a few questions to presenters. I will remind that please ask questions in the chat. It's still relevant, and especially for the last presentation, we didn't get any questions yet. But I would like to start with Maria. I see that she is switched on her camera, so if you can switch on microphone. Yes. Hello?
Hello.
Can you hear me well?
Yes.
Yes. Thank you for presentation, and we got a couple of questions to you. So the first question was, is there a chance to decompose the streaming potential into the constituents of the rock? What do you think about that?
So I think you probably need first to get the response from like clean mineral samples, and then maybe with the patched model you could interpret the response from natural samples that have chemical heterogeneity. That's my guess.
Yes, thank you. And there is a question from the studio. So why is the EPM of Indiana limestone and calcite is so different?
So as I also mentioned in the presentation, we think it's because in electrophoretic mobility measurements, you basically crush your sample to like very fine powders, and then you create new surface sites that they are exposed to solution, and those surface sites are not exposed in streaming potential that you have an intact sample. And I also think it could also be because of the equilibration procedure. Streaming potential is a closed setup, so basically your system it's not in equilibrium with the CO2 phase. Yeah.
Yes.
So that's why I really think when we compared these measurements, it would be really good to properly characterize the solution composition to make sure that the systems are similar. Yeah.
All right. Thank you very much for a detailed reply. And I would like to move forward to Hassan Mahani. Thank you, Maria. So, Hassan, if you can switch on your microphone. Yes. Can you hear me well?
Yes, I can.
Okay, we can hear you as well. Very nice to see you again.
Same here.
Yes, thanks. Thank you very much for presentation. And you seem to be the so far the most popular guy. You get the most of the questions. I see that you replied most of the questions in chat, but it would be nice if we can comment on these questions online as well, right? So the first question was, what is the effect of roughness on wettability alteration in smart water injection?
That still has to be done, actually, because there are not many studies on this. My feeling is that because of the roughness, the water film thickness could be large, which separates the oil from the mineral surface. Therefore, the interaction forces between oil and rock may be much weaker compared to the cases where the roughness is less or surface is quite smooth. So, but still, we have to do experiments to really verify this hypothesis. I know amongst the answer there were some opposite opinions that roughness may improve low salinity effect, but that's what I could follow from some other numerical simulations that we have done recently.
Okay, thank you very much. Next question. Next question was, since the low salinity water flooding effect is highly dependent on temperature, is there microfluidics experiments able to be performed at representative reservoir temperatures? So what do you think about that?
Of course, it's doable. And we are working on that to start testing at elevated temperature. But I think beyond 100 degrees Celsius, it could be challenging because the two plates of the micromodel are glued together, and stability of the glue and the pressure increase due to the evaporation of liquids at higher temperature may pose some challenge. So we have to look into that. But in principle, that's possible if we use a HPHT kind of setup to do it. And that would be really interesting to see whether we see improvement or impairment of the response.
Thank you. The next question to you is, it seems that the average pore size is in your experiments is greater than the typical the pore size of the rocks or calcite. Yeah, roughly speaking, what is the average or range of capillary number for the conducted experiments?
Yes, indeed. The average pore size was around 300 microns. We had, of course, smaller pore throats and also larger pore throats. That's kind of average. So we had a distribution, definitely. And that was just to start the work. Hopefully next time we can go to narrower pores such that we can look at more tighter kind of carbonates. For the capillary number, we made sure that it's less than the capillary desaturation threshold, which is about 10 to the minus 5. So whatever we observe in terms of low salinity response is definitely not related to desaturation. We flooded the system actually for several pore volumes and nothing happened. We observed the same thing in sandstones. Whether it was clay coated or a bare silica micromodel, we saw almost the same thing in terms of what we observed in terms of time scales and also desaturation effects. So definitely reduction of capillary pressure and allowing some time for a spontaneous inhibition in the process is really necessary to have all these electrokinetics phenomena, which are time dependent, occur, mainly in the water films that are underneath the oil.
Thank you very much, Hassan. And Tina, could you please remind me how much time do we have?
Enough time.
It's enough time. Okay, then I will continue with Hassan if it's okay.
Sure.
The question from studio, from us here. So have you verified the results, especially the results with the silicon nanoparticles in actual core floods?
We are going to do that. We are going to, as part of an industry project, we are going to do that. Because one of the concerns is injectivity of this nanoparticle augmented brine. So we have to look into that. But in terms of seeing the effects at micro scale, we're quite positive that something positive is going to happen with it in terms of oil recovery.
Thank you for the answer. And we have a last question to you. So what is the relative significance of the change or delta in contact angle versus the final wetting state in improving oil recovery? So for example, would a larger change in contact angle, but still within the oil wet state, enable higher recovery compared to smaller change in contact angle, but within the water wet region?
We still have to find experimental data supporting this. But that's a very good question, actually. What we have seen from the micro scale experiment is that contact angle change by itself is not enough to produce oil. It's also necessary to detach the oil from the mineral surfaces and then mobilize it. If this is not going to happen, nothing is going to be produced. And in addition to that, even if you produce oil or mobilize the oil, we need a good drainage process to occur. If this mobilized oil is get trapped in let's say, in the upfront pores or throats, then nothing will get produced. So in addition to contact angle changes, we need a good drainage as well. But to find out whether water wetting or oil wetting would be the most suitable conditions for oil recovery, there are some data which suggests that potentially systems with initial wettability close to oil wetting state is more preferred compared to water wet systems.
Yes, thank you very much, Hassan, for detailed discussion and answer to questions. And I would like to move forward and talk to Motas, if it's possible. So if you can unmute your microphone. Motas, can you hear me?
Yes, I can hear you well. Can you hear me?
Yes, we can hear you well. So thank you very much for a good presentation. And we got a few questions to you in the chat lately. So the first set of questions was, how do you model surfactant adsorption in STM? And also, how do you account for DDL expansion due to surfactant adsorption, for example? And does it stick through bridging mechanism only, or it is allowed to interact with positively charged sites as well? So please, if you have any comments about that.
Yes, thank you for these questions. Although I didn't have the time to go through the surface reactions related to the surfactant, but for the double layer expansion, we actually treat the surfactant, which I showed for the anionic, as a negatively charged ion. So it's similar to the way that, let's say, a sulfate would interact with the calcite surface. And for the results to match the zeta potential experiment, we manipulated the charge number of the surfactant for the anionic, and it showed -2. So it's kind of like a divalent anion. So that's how let's say the surfactant molecules or as an ion are modeled. And as for the expansion, it has a slight effect on the screening. So you can think of it as 1,000 ppm, so that will slightly change the debye length to make it small, but we looked at it at a different interface for the crude oil and the calcite surface separately. This is for the first question. And for the second one, does it stick through bridging mechanism or only it's allowed to interact positively charged sites? Yes, for the anionic, since it is negatively charged, we look at it from, which is a simplification, of course, from electrokinetic standpoint. So for the anionic surfactant, it only interacts with the positively charged surface. We did also I did some results of modeling for the amphoteric, which is mainly, it has more positive components, and it interacts with the negative components of the calcite. So there is no other mechanism besides the positive, let's say, amphoteric will interact with the negative parts of the calcite, and the anionic, the negatively charged, would interact with the positively charged component of the calcite surface or the crude oil surface as well.
Thank you very much. And we have one more question from the question and answer chat. So how do you think about direct adsorption of polar components from oil onto the rock surface? Do you assume you have always the water film available?
Yes, that's a good question. Yes, I always assume there is a water layer sandwiched between the two surfaces, the crude oil and the calcite. And they're completely both, I treat them as separately. So, which is a simplification. If they get close, there would be other, let's say, mechanisms such as asphaltene adsorption or not. But in this study, we do not take them into consideration. We treat the calcite surface separately and the crude oil adsorption of the surface reactions separately. But definitely there should be further mechanisms, especially for the asphaltene component adsorption.
Thank you very much for a detailed answer. And yes, so it seems like we don't have any more questions. So thank you, Motas. And I would like Skule to come maybe and comment a couple of things and close the session. So as Michael wasn't available for questioning, so we have a question to you, Skule. So how do you see the future of using polymers, for example, in combination with the smart water or in like polymer injection itself? So with the increased focus of environmentally friendly techniques, so what do you think? What's the future of polymers in this case?
Yeah, I have a little bit problem to understand. There is a problem with implementing polymers, and from an environmental point of view, there have been some trials on more environmental friendly polymers. But it don't seems to be a big success. There is biodegradation that is a part of the problem with implementing these polymers into reservoirs. So from an environmental point of view, if you need a lot of bacterioseeds together with your polymers, it don't necessarily help on the environment. And there is an extra cost with, I think the biggest issue regarding polymers is the cost. And with lower oil prices, it's not, it could be difficult to have a good enough economy of implementing polymers. That's my understanding.
Thank you, Skule, and maybe if you have final comments regarding the session. So
no, I think it's been a little bit interesting session, and we haven't worked very much with the surface charges and streaming potential, but what I've seen over quite a lot of years that the streaming potential is in a way something that people are talking about, but it's still a lack of good results confirming the efficiency of streaming potential to be able to use it as to describe surface charge processes. And definitely, we have to remember that the brines that we are working with, it's a formation water, contain a lot of calcium and magnesium ions. And when we try to model these processes, we often only say that, okay, ionic strength. So instead of having one magnesium ion, I say that I only have 2 sodium ions. And for us working with reservoir chemistry, it's maybe too simplified approach to be able to do it. So we need, if you're going to do streaming potential measurements, we need to work with real brines containing typical brines of a formation water with a lot of calcium and some magnesium ions also included. So theoretical brines with a ppm is not enough.
Thank you, Skule. And I guess there could be still continued discussion in the chat. But we have 15 minutes break and continue with the next session at 3:30. So thank you for attention and see you in 15 minutes.
welcome back. I hope you had a nice break and that you are now ready for the next section of today. So the second topic today is on core restorations, measurements and modeling of wettability. Our first presenter will be Ingebret Fjelde from Norse, and he will present effects of mud exposure on established wettability conditions. Ingebret Fjelde is a research professor in the IOR Skule group at the Norwegian Research Center. And his main research interests are water-based and gas-based enhanced oil recovery methods, EOR methods in sandstone and carbonate rock, formation damage and mechanisms, and CO2 storage. He holds a master degree and a PhD in chemistry from the University of Bergen. Please, Ingebret. I hope you're with us.
Yeah, I'm here. And I'm sharing the screen now. Can you see it?
Yes.
Yeah, okay, then I can start. So my presentation is on the effects of mud exposure to established wettability conditions. I will show you a few examples related both to, or related mainly to sandstones. I'm not including carbonates in this presentation. So if we know that in the reservoir we have equilibrium between the rock, brine and oil at the conditions that we have there, and we want to re-establish the conditions in the lab. And of course, when we're taking up our rock samples, we are changing the temperature and pressure, and in that way changing the solubility of many components that we can have in the samples. In addition, we may have mud contamination, and if we want to have a representative rock sample, it's also important to store the rock samples in a proper way. And of course, we would change the wettability when we are cleaning it. We also need a crude sample that is not contaminated or oxidized, and we need a representative brine composition. So first I will show you two examples related to water-based mud and how we can determine whether the reservoir rock is contaminated by the mud. So in my example one, we got some reservoir core plugs from a field on the Norwegian continental shelf. The coring fluid was a KCl mud, and we injected synthetic formation water to the rock samples. And we had 4 different core plugs from C1 to C4, and we measured the effluent potassium concentration when we injected the synthetic formation water. And we can see that we are starting at extremely high potassium concentration and is gradually going down. What we should end up with is the black star here, which is the concentration of potassium that we are finding in the formation water, which is approximately 350 ppm with potassium. So it's clear that this sample was contaminated. We can also see it from the sodium concentration in the effluent, that we have much lower sodium concentration in the beginning because the formation water had been displaced by this potassium chloride mud, but it's increasing and coming up in the range where we should end up with is the black star again, which is the concentration of sodium in the formation water. We got similar profiles for calcium and magnesium. So it was clear for us that these core plugs were contaminated by this KCl mud. Then we cleaned the rock samples, and we analyzed the cleaned rock samples with scanning electron microscopy, and found that there was clusters of clay and polymers and pyrite inside the rock samples. And we looked at the especially the barium concentration. We see that it's clearly showing that we have pyrite inside the rock samples. So even after cleaning, we were not able, we were able to see these clusters of mud components. So we were not able to clean and remove the mud particles. Invasion of particles and polymers can reduce the permeability. That's one effect of the invasion. But if we have invasion of a clay, we will also increase the surface area. And we know that often clay is one of the most oil-wet minerals that we have, and in the rock. And if we have more minerals, clay minerals, and then increasing the surface area, this may affect the established wettability conditions. We also got core plugs with a lower permeability from external lab. And again, we saw that the potassium concentration when we injected the synthetic formation water was much higher than it was in the real formation water. You can see the blue squares here, which is the level of the potassium in the formation water. If we have earlier looked at the effect of potassium chloride on oil adsorption, and you can find a reference here back to 2013, where we looked at the effect of potassium on adsorption of polar oil components. And potassium is forming weaker complexes with carboxylic acids than the divalent ions that we are often finding on clay surfaces, for example, calcium. But when you have very high concentration of potassium, it's able to displace the also calcium from clay surfaces. Then I will say something about results from studies on oil-based mud and the effect of mud filtrate exposure. First example is oil-based mud, where we have an asphalt product as a fluid loss additive. And after the exposure of the rock samples to either a mud filtrate with a mineral base oil or mud filtrate with a synthetic base oil, at the initial water saturation, we injected the stock tank oil and measured the interfacial tension. And the interfacial tension between the stock tank oil and synthetic formation water was approximately 25 millinewton per meter. But when we started to inject the stock tank oil, we had much lower interfacial tension in the effluent. And it's clearly showing that we have a contamination of oil-based mud. And then we injected the stock tank oil until we reached a stable delta P across the core. But you can see that the effluent samples are saying that there are still emulsifiers released from the core samples. Then we measured the spontaneous imbibition of synthetic formation water. And you have the oil saturation here on the y-axis and the time on the x-axis. And you can see the sample with high spontaneous imbibition of water is the sample without any mud exposure, is the dotted line here. 2 samples with exposure to mud filtrate had a lower spontaneous inhibition of the synthetic formation water, showing that they are more oil wet. So in this case, the core plugs exposed to mud filtrate became less water wet. Then I will show you another example where we used an oil-based mud without asphalt products in the mud. Then we prepare the core plugs at initial water saturation and aged it with crude oil. Then we exposed one core plug to the mud filtrate, and the other we didn't expose to mud. And after the exposure, we had a mild cleaning, injecting the stock tank oil to both exposed and not exposed core plugs. And then we measured the spontaneous inhibition of the synthetic formation water. And we have oil saturation versus time. And you can see that the red curve is the core plug with mud exposure. Had a higher spontaneous inhibition than the core plug with no exposure. So for this type of mud, the mud exposure gave a more water wet rock. Then we did a similar study, but in this case we prepared the core plugs at initial water saturation, exposed them to or aged them with crude oil, and then exposed one of them to the mud filtrate, and the other was not exposed. Then we cleaned the rock samples with toluene methanol and re-established the initial water saturation, and then aged it again with crude oil. And then we did spontaneous inhibition experiments with synthetic formation water. And again, we can see that the red curve here for the mud filtrate exposed core plug gave more water wet conditions than the core plug without any exposure. So again, the mud filtrate exposure gave a more water wet rock. So in conclusion, I would say it should always be determined whether the reservoir rocks are contaminated by mud or the coring fluid. But then we have to know the type and composition of the mud or coring fluid that have been used. So we should, the lab should require that when we get a project from the oil industry. If the reservoir rock is contaminated, it should ideally not be used. But if you have to use a contaminated rock, then you should confirm that the contamination are removed, or to what extent the samples are containing mud contaminations. And then we can say that mud contamination can give wrong wettability. It can either be more water wet or oil wet than it should have been. I would say also at the end that it's better to know where core preparation was started than to search for reasons after unexpected results are obtained. Because if you know that your core samples are contaminated and you can select other core plugs that is not contaminated, then it's better to use the non-contaminated rock samples instead of doing a lot of work that may cost millions and then end up with very strange results. And also, if we have different starting point for the prepared reservoir core samples, it may cause scattering in the results. And that's also important to keep in mind, that if we have non-contaminated samples, we are starting at least without contaminations that can affect the wettability. Okay, thank you.
Thank you, Ingebrigt, for your nice presentation. The next speaker is Ivan Piñeres Torrijos from University of Stavanger. He will present reproducing wettability in laboratory core restorations and the influence of solvent cleaning on carbonate wetting. Ivan holds a master's degree in chemical engineering from University of Barcelona and a PhD in petroleum technology from University of Stavanger. His main research topics are reservoir wettability and smart water IOR processes in both carbonate and sandstone reservoirs. He has participated in fundamental research to improve chemical understanding of reservoir wettability and wettability alteration processes in many projects with objective to evaluate IOR potential for specific oil reservoirs with smart water. So please, Ivan, the floor is yours.
Thank you, Tina. So as it was mentioned by Tina, the title of this work is Reproducing Wettability in Laboratory Core Restorations and the Influence of Solvent Cleaning on Carbonate Wetting. So here we're gonna give it a twist to this presentation, and we're gonna start by the results to show you the achievement. So what we have achieved was wettability reproduction in a second restoration in relation to the first restoration on carbonate under a spontaneous imbibition process. So you can see in the figures 4 parallel sets of cores, and the first restoration is indicated in continuous lines, and the second restoration is indicated in dashed lines. And what we found was that the wettability was reproduced with a very low error of approximately lower than 5%. We reproduced not only the ultimate recoveries, but also the spontaneous imbibition profiles and imbibition rates, which was very positive. And this was achieved independently of the specific core heterogeneity of the cores used. So now I'm gonna explain to you how we achieved this. So we know that in the carbonate reservoirs, the polar organic components in the crude oil, and especially the acidic components, have a large impact on wettability. And we know that as the acid number increases, the water wetness decreases, and it affects the imbibition rate and the ultimate recovery. This is valid for both real crude oils and model oils, as you can see in the figure. The materials used in this presentation were basically a chalk, very pure chalk that came from the Stevens Klins quarry in Denmark, and we know that this material is an analog for North Sea reservoirs. We have used as a brine formation water brine that was based on a North Sea oil reservoir, but it was depleted in sulfate to not induce wettability changes. And as crude oil, we had used a model crude oil. The first thing that we did was to test the initial wettability of this cores. And what we found, in the blocks that we had studied was that the behavior was strongly water wet. In the figures, you can see a spontaneous imbibition test done with heptane, and we observed a very fast process where more than 90% of the model oil was expelled out from the cores in less than an hour. So then, in the process of core restoration, we had to compare 2 different processes. So we compared a mild cleaning system that was composed of a kerosene and heptane, and a harsh cleaning system which was composed of toluene and methanol. We know that the mild cleaning system will remove the residual oil, but it will also help us to preserve polar organic component that was adsorbed onto the surface. So the mild cleaning should not alter significantly the oil wettability. On the other hand, the harsh cleaning method uses solvents that are more aggressive and they have a higher solvation power. So we were expecting these polar components to remove more adsorbed polar components from the surface. And then the experiments followed in the following fashion. We just restored the cores with crude oil using 5 pore volumes of crude oil, and they were imbibed under standard spontaneous imbibition. And we obtained very similar oil recoveries at that point, indicating that the wettability changed to a less water-wet system. Then we cleaned the cores with the different methods, and what we found was the mild cleaning preserved more of these polar components and yielded a lower oil recovery in comparison to the harsh cleaning method, which removed substantially more polar components and gave a higher oil recovery. Another point that we had to pay attention was the amount of crude oil used during the core restorations. So in the plot, you can see that in the continuous line, we have the first restoration. And in the dashed line, we have the restoration after using 5 pore volumes of crude oil injected. So the result was that this excessive amount of oil reduced the wettability in this second restoration. We tested this in different experiments, and we found that by using an excessive amount of oil, was giving large differences in the wettability. So the crude oil was also important. So up to this point, we have learned that the mild cleaning preserved more polar components than the toluene methanol cleaning process. We also realized that the wettability was highly dependent on the crude oil injected into these cores during the restoration. And we also saw that the harsh cleaning created more variations in between the restorations. So the key points to achieve the wettability reproduction on carbonates in a spontaneous imbibition test was to use the mild cleaning process. And in second place, we had to control the amount of solvents to be injected. That means controlling the kerosene and heptane injected. And we also had to control the crude oil that was injected into the cores. So the strategy for the wettability reproduction was to reduce the amount of kerosene injection to 10 pore volumes. We also reduced the injection of heptane to 5 pore volumes. We shortly injected distilled water, and we saturated with 0.9 pore volumes, or 1 minus the initial water saturation volumes of crude oil. And this led us to the results that I showed previously, with a very low error in the reproduction. So the conclusions of this piece of work is that both the cleaning methods remove fractions of adsorbed polar components, but however, the mild cleaning method minimized these changes. And we also think that the rendering the cores to a completely water-weight behavior removes important information that is linked to the initial core wettability. This is due to the fact that the oil that initially wetted the reservoir might differ from the oil that is present in the reservoir today. In addition to that, the wettability reproduction was achieved by minimizing the injection of mild cleaning solvents and with the combination of minimum exposure of crude oil. Apart of this, we know that these results represent a successful milestone to obtain closer estimates of initial reservoir wetting in carbonates. And that this strategy that we had put forward can help to as a new alternative way for advanced core analysis. Yeah, and so with that we finalize, and here are some acknowledgements. We appreciate the effort of the students and all collaborators of this work, and we also thank to the partners and sponsors of the IOR Center and the University of Stavanger. Thank you.
Thank you, Ivan. Very, very nice presentation. So we have one last presentation in this section. And that presentation is by Ali Aftekhari from the Danish Hydrocarbon Research and Technology Center. He will present a mathematical model for better core scale analysis and faster field scale simulation of modified salinity water flooding. Ali studied chemical engineering, petrochemical processes at the Sharif University in Iran, and transport phenomena and separation processes in Sharif University of Technology in Iran. After that, he worked as a freelance process engineer and process simulation and optimization instructor before pursuing his PhD studies on low emission conversion of fossil fuels at the Delft University of Technology. Afterwards, he worked as a postdoc at TU Delft, studying the application of nanotechnology in enhanced oil recovery. And then he worked as a postdoc researcher in the Center of Oil and Gas at DTU in Denmark. So please, Ali, the floor is yours.
Hi, my name is Ali Aftekhari. I'm a researcher at the Technical University of Denmark, and it is a pleasure to present part of our work on the mathematical modeling of modified salinity water flooding for better analysis of core-scale experiments and faster simulation of field-scale trials. The work is done mostly by our PhD students, Mira Saint-Taheri and Maria Bonto, under the supervision of myself and Dr. Hamid Nik. So what is the current practice when we want to model modified salinity water flooding? So basically we take a core sample from the reservoir or from an outcrop, and we clean it, we saturate it with oil, restore it to reservoir condition, inject either formation or seawater, and produce some oil, and we get some data points. Then we feed a semi-empirical model, it is extended Darcy's law, that usually has 6 to 10 parameters, and then we call it history matching. Then we can use that model, of course, for the modeling of the whole reservoir. And when it comes to modified salinity water flooding, we inject a new brine that is with the modified salinity. We get some more oil, and then we history match it, get another 6 to 10 parameters, and then again we feed it to the reservoir, and we can model the whole process. So when we flood a core, the injection brine replaces the formation brine, and the formation brine pushes oil that is mobile at the beginning, and we produce it, and we record all these data points. And at the end of this experiment, we start injecting a new brine that is going to first of all disturb the equilibrium between the formation brine and the rock, so we are going to have some ion exchange. Therefore, part of the brine will be depleted of certain ions because these ions are adsorbed on the surface of the rock. And then some of these brines that we have here are going to mobilize oil that has become immobile at the end of this experiment. So which one of them is going to do that? Is it right on the front here? Is it here? Or is it here? We don't know, but it's very important because this delay that we observe in the production here, it can be translated to a few years when we go to reservoir scale, and that becomes important. It is something that is observed before in the lab, for instance in the experiment of Gupta and all other experiments in the literature. And we want to basically understand where this delay comes from. So that was the big picture, but what happens in smaller scales? So we have a core scale that we saw, then we have what happens in the pore-scale, the interaction between interfaces that are translated into mobility. And then if we zoom further in, we can see all the interaction between the interfaces, and finally the interaction between molecules and ions. And it is really difficult to, first of all, describe all these interactions using core flooding. So in my opinion, core flooding is bad science. And also we cannot really put all of this into our mathematical models because it makes things really, really slow. So we have to simplify things. So based on all those physical interactions in different scales, we can create a conceptual model. So we can look at the Darcy scale, look at small pores in micrometer scale, and then here we have different phenomena happening. So we have adsorption of ions on the surface. That's something that we can model in the Darcy scale. And then when the brine reaches here, all the ions have to diffuse into this water field that we have here between oil and the rock surface. So if we zoom in on this part, we have a formation water film. That's a very thin film, and it is usually observed that diffusion in this water film is much slower than the bulk diffusion of ions. And the reason is that there are also electrical potential profiles here. These are going to slow down diffusion process. Also, the water film here, it can be packed with ions, and therefore it's going to reduce the molecular diffusion a couple of orders of magnitude. So based on that conceptual image that we created, we write a mathematical model. So we go with two sets of relative permeabilities, one for formation brine and oil, the other one for the injected brine and oil. And then to interpolate between these two, we go ahead and model the diffusion of potential determining ions. It can be any of the ions we don't choose. The diffusion of these ions into the water film. So we assume that these oil blobs that are remaining in the system and are a function of oil saturation, they have a length of few to hundreds of micrometers, depending on the pore shapes that we can get from imaging, for instance. And then based on how long or how far these ions have diffused into this film or adsorbed on the surface, divided by the initial length of these formation water films, we find an interpolating factor that interpolates between these two sets of relative permeability curves that we have. To model the physicochemical interactions between rock and brine, we fit a surface complexation model to zeta potential measurements and also chromatographic measurements. We optimize all the equilibrium constants of the surface complexation model such that it honors all the signs of zeta potential measurements from electrophoretic mobilities and the actual concentration of the effluent of a chromatographic experiment. And to make things faster, because the surface complexation model can be rather slow when we solve the full chemistry, we try to fit a Langmuir isotherm into computational data that we generate for different systems using our optimized surface complexation model. Since our model is already published, I don't go into the details, but just mention that we use FreakC and a wrapper in Julia programming language to do the fitting and optimization of surface complexation parameters. Relative permeability parameters also we fit using analytical solutions, and we solve all the partial differential equations, both two-phase and single-phase, with the finite volume package that we have written in MATLAB, and it's open source. So you can find the details in our paper. To verify the model, we extracted lots of core flooding data from the literature, and here is one sample from the paper of Gupta. They did some experiments, and as you see, we tried to model it without including adsorption and diffusion in the model. And as you can see here, we cannot really predict the delay that is observed in the experimental data, no matter what we do with all the relative permeability parameters. However, as you see on the right side, when we include adsorption, we get slightly closer to the actual breakthrough time of oil, and when we include diffusion controlled adsorption in the water film, we can very well fit the experimental data, as you can see on the solid black line. To conclude, we have a bunch of models, all of them are wrong, but we can make some of them useful by including a little bit of more physics. And the core flooding experiment, in my opinion, not bad science, unless we analyze them carefully and with the right useful type of models. And we observe a major delay in the response of cores to the modified salinity water that is injected into them, and that delay cannot be directly translated to the field scale. So it means that we have to expect a faster response in the field if we use modified salinity water flooding. So these are some references that goes into more details about what I just said, and we have most of the codes published online as open source. I would like to thank the DHRTC Advanced Water Flooding Program for funding this research. Also, I would like to thank the organizers for giving us the opportunity to present our work here, and thank you for your attention.
Yes, thank you all the presenters for the interesting talks in this second session. And now I would like to have some discussion and ask some question from people from online. So if Ingebret, if you can unmute your microphone and answer a couple of questions, that would be nice. Can you hear me?
Yes, I can.
Yes, hello. Yes, thanks again for the nice talk, very interesting presentation. From myself, I can say that we also observe the effect of mud contamination on the reservoir cores. And it's, I think it's very interesting and important problem, which has to be taken into account, absolutely. And so we have a couple of questions in chat. The first question was that why did it take 6 pore volumes to get to expected concentration while breakthrough usually happens at 1 pore volume? So I guess it's a question regarding the production of potassium during the your injection.
It's so that if you are injecting a tracer that is not interacting with the minerals, you will expect 50% concentration after injecting 1 pore volume. But if you have ion exchange, as you have in this case, when you are injecting synthetic formation water with very low concentration of potassium, the calcium and other divalent cations will replace the potassium that you have on the clay surfaces, for example. So it will take a longer time to get all the potassium to the level that it should be with synthetic formation water. So it's really the effect of ion exchange.
Yes, thank you. And the next question, can you once again clarify the significance of the contamination by mud to oil recovery? So how could you summarize it, let's say?
Yeah, you see that I showed you some spontaneous emission curves. And you see that in a spontaneous emission curve, you have the oil saturation that you will have after the spontaneous emission. So you clearly can see the effect of mud contamination. It's also known that the relative permeability curves and thereby the residual oil saturation in viscous floods will depend on the wettability. So that's something that we also are looking at. But it's clear that wettability is affecting the oil production.
Yeah, thank you. And a question from studio. So what would you suggest then? I saw that you said in the conclusion part that yes, so better not to use if you can avoid using the core contaminated by mud, so better go for it. But if you don't have opportunity and you have to use these core samples, then what would be your suggestion regarding the core cleaning to end up with the most representative core sample for further studies? So maybe we should flood the low salt brine, for example, to get rid of the potassium at the first place, or what would you suggest?
Again, it's depending on the type of mud that you have. You have water-based and you have oil-based, but also within water-based and oil-based, you have different types of mud again. So I showed you the example where you have asphaltene products as a fluid loss additive. Of course, if you have a mild cleaning there and you're injecting, say, kerosene and or heptane, then you will not get anything of this out of the core. It will just stay inside the core. Mm-hmm. But if you then using, say, a solvent with a higher aromatic content, you will also dissolve these asphalt products. But it can take a very long time because it's not these products is containing molecules in a large range. It's natural products that are used. So it's easy to remove the smaller molecules, but it's more difficult to remove the aggregates or larger particles of these asphaltene products. So I will say that it's important to know what type of mud that you have. That's the first point, and I don't understand why it should be so secret as it is in many cases.
Yes, thank you very much for your comments. And now I would like to speak to Ali, if it's possible for you to switch on your microphone. Can you hear me?
Yeah.
Yeah. Hello, thanks for the nice presentation. Maybe it was a bit complicated, at least for me, so and maybe for the audience as well. So not too many questions so far, at least. But the question to you in the chat was, what are the novelty of the future work and validate with experimental work? So how can you comment on that?
Yeah, thank you, and thank you for the question. I'm not quite sure if I understand it, but let's say, yeah, in terms of novelty and what we can add to this work, we right now we don't have really any link between the model that we have that somehow can represent the diffusion control adsorption on the surface of a rock that is covered by oil. So that's something that we can model, and also there are new experimental evidence by, for instance, Hassan and other people coming out that basically confirms the model that we have, but we don't know how to link it to two-phase flow in porous media. So that's something that we hope we can model at some point mechanistically, not by using correlations. So that's something we hope to do in the future.
Yeah, thank you very much. I hope you get more questions in the chat so you can reply to people. Otherwise, thanks for the presentation. And we move to Ivan, who is with us in studio. And you get quite a few questions. So let's start with the first. And different people ask you a question regarding the initial water saturation. So the question was, what was the carbonate core permeability to reach connate water saturation of 10%? I guess it's quite a low value. And the second question was, when hash cleaning, did you always desaturate to the same residual water saturation? So can you comment on that?
Well, I first need to say that in this type of laboratory core restorations, we're working with the desiccator technique. And the desiccator technique is quite convenient to achieve a specific initial water saturations. And that helped us to design in a very good way, you know, all the experiments, because we can change only one parameter of our system and see the real effect. In this case, the core material had a permeability that is pretty low. All cores were ranging from 1 to 10 millidarcies. But even in this low region of permeability, we can work without any problem, you know, to achieve stable water saturations. And we have to work with the same method for the mild cleaning process, you know, and in between restorations. So the question related to the harsh cleaning didn't, in that aspect, we had the same protocol for everything, so there was no problem for establishing.
The second question was regarding the cleaning process, yeah? So how do you know that with toluene you reverted the wettability back 100%?
Well, now I know that the person who asked, you know, like, was reading a statement, like in that statement we were relating it to the standard protocols, where the standard protocols, they aim to render the course to a completely water-weight situation. In the case of the study, we reverted almost 90%, but we didn't revert it in 100%. So this was more a general comment, rather than very specific to this work. But we have observed, that this pair of solvents was solvated with much more efficiency than the mild cleaning process. And then in that way, we saw different changes in wettability as we clean it. Yeah, they were becoming more water wet, and as we were introducing again the crude oil, they were lowering again the wettability. So there were more changes, during the entire process, by using the harsh cleaning method.
Yeah. Could you also comment, please, on aging process of this course? So did you focus only on studying the wettability alteration using the cleaning process, or how the aging would affect?
Well, I need to say, that this is a result not only of this piece of work, but it's a result, from studying smart water, for several years, and reservoir chemistry. So when we started this work, we knew that in this type of material, the crude oil absorption was occurring immediately. So that was reported by researchers like Hopkins and Mios, where we observed that these polar organic components were immediately absorbing and immediately affecting the wettability. However, we proceed with some specific amount of crude oil to be injected into this course, knowing that this absorption was almost instantaneous. But we added also for all course an aging process, that it lasted longer, than the experimental time of the spontaneous imbibition process to assure uniform conditions, in all cores.
Yeah. Then another question was regarding the crude oil which was used. So first of all, what kind of crude oil, modified crude oil, was used to do these experiments? And how do you think the reservoir crude oil would affect the results if we would use the more complex reservoir crude oil? And also regarding that, how the oil saturation of the core samples was occurring. The comment was that by centrifuge or flooding method, and definitely centrifuge method is preferred, so by one of the person's opinions. So how can you comment on that?
Well, so the first question, I need to mention that in my second slide, I showed the effect of real crude oils and model crude oils. These model crude oils were based, is a combination of some additional solvents with real crude oils. And probably during the presentation, I also mentioned that we had used heptane in some of the stages for especially to measure the capillary forces in the first state. But that's only to test, the capillary forces, of the course at arrival. But during the entire process, we can literally say that we were using crude oils, that were combined with some solvents, but they have a very similar composition to reservoir crude oil. And can you remind me the second question?
The second question was, how was the oil saturation happening by the centrifuging or by the flooding? And people believe that centrifuging would be definitely preferred method in this case. What do you think?
Yeah, well, in this piece of work, what we had used was a flooding mechanism. We initially established initial water saturation in this course with the desiccator method. So we were sure that all cores, when it had precisely achieved this 10%, and then we flooded this crude oil in the first restoration. We had used 5 pore volumes in the first one, and then by achieving the wettability reproduction, we had to minimize this amount, and then we use a different setup where we sort of imbibe, the crude oil into this course.
Thank you, Ivan, for good detailed answers. And you have a couple more questions which you can reply in the chat of Zoom. And thank you once again for all presenters in the first part of the second session. And we have a 10 minutes break. And see you all in 10 minutes. Thank you.
Welcome back to the second session of wettability and impact on core restoration and modeling work. So first, remember you have the possibility to do some questioning for the presenters. So to use the Q&A or the chat. So, and keep Alexander busy. Okay, the first presenter in this second session is Asier Pandero from CEPSA. And the title of his presentation is Experiences of Numerical Simulations Impact on Permeability Curves Determination. Asier is a researcher at CEPSA Research Center in Madrid, Spain. He holds a degree in chemical engineering by Universidad del País Vasco and a master degree in oil and gas engineering by Universidad Politécnica de Madrid. He is currently focusing on tracer technologies and IOR research projects. The floor is yours.
Hello everyone, I am Asier Panadero from CEPSA. Thank you for attending to this presentation that is called Experiences of Numerical Simulation Impact on Permeability Curves Determination. We are going to see how the use of numerical simulation improved our laboratory results in two examples, interpretation of multi-step and state-state experiments, and the use of numerical simulation for design of experiments. First, we have an experiment that has two different stages. First, a forced water imbibition, followed by a forced oil drainage, both multi-step. During the experiment, we recorded the differential pressure and the oil production by mass balance. And with this data, we obtained the points that are plotted in the graph. Labeling blue the imbibition ones and labeling orange the drainage ones. With these points, we obtained also the Corey exponents that fitted these points, and that was our analytical solution, the combination of the points and the Corey exponents that fitted them. So, what came then? The reinterpretation of the experiment using numerical simulation using the software CDAR. What we did is a history matching process of the imbibition part of the experiment. We history match the oil production and the differential pressure. We can see in the graphs the red points are the obtained laboratory data, and the black line is the simulation solution given. So, how did the numerical simulation change our solution, our result? Here we have, in the graph at the left, we can see the new curves obtained by simulation that are the solid lines. We can see that they are slightly different than the previous ones obtained analytically. And as the simulator takes into account the physics of the process, not only the record of two variables, and the capillary pressure curve has an impact in these calculations, we also estimated it. An important part is related with the determination of the capillary end effects. We know that the capillary end effects are present in our core fracking experiment, and it's something that was present at field scale, so it's critical to determine them. These capillary end effects can be determined by in situ monitoring techniques during the experiment or using numerical simulation for the interpretation. That was what we did. We can see in the graph at the right the profile of water saturations during the experiments and along the core. In the x-axis, we have the distances from the beginning of the core to the end, and in the y-axis, we have the water saturations. The red dotted line is the water saturation, the final water saturation that we obtained by mass balance. We obtained a value that we assume it was the same for all the core, because we analytically we couldn't determine that end effects. Once the end effects are determined, we can see that this value or average value obtained by mass balance is not the real one. We can see that at the entrance of the core we have higher water saturation than at the end, and if we discard that end effect, the final value that we should obtain was the one at the entrance was higher than this average value that was obtained by mass balance. The difference in our case was 5%, but we know from bibliography that this difference can be as high as 15%, so it can have a huge impact. A critical point to determine the capillary end effects. We can see also in the graph at the left how this difference in the saturations, the one that are assumed by mass balance, or what we call the average solution, is different from the final one. We can see in the green solid curve, that it's the simulation one, how the endpoint for the saturation is higher than in the analytical solution. So our conclusions are that the history matching allow a more accurate determination of relative porosity curves. The simulator takes into account more physics of the process than only the monitoring of two variables. The capillary pressure curve was estimated. The capillary end effects were determined, and the correction of the residual oil saturation that is related with this determination of the capillary end effects means more oil is recoverable with water flooding. We have finally the experiment's design. We wanted to perform an experiment for relative permeability curves determination, so we planned a multi-step and steady-state experiment, and we took reference relative permeability curves for our first simulation. That was the simulation of that planned steps, and what we predicted is a high water saturation even at low injection rates. That was not a proper solution. That was not what we were expecting. That was a wider rates for saturation, lower saturations from the beginning. So we switched our experiment for a compromise between a steady state and a steady state. We repeated the process, we performed that simulation, and we obtained a better prediction because lower water saturations were obtained at the first steps. That was the plan that we implemented, that we will follow. But during the process, after each of the steps, we performed the history matching of the previous steps, and we readapted that planned steps of the steady state and steady state experiments. So what we finally obtained was an iterative process, but we readapted the following stages, and finally we did a final history matching to obtain the better solution. So our conclusions here are that the simulations in the design stage allowed an optimization of the experiment, as high water saturations were predicted. And we're using only a steady state experiment. We switched it to a steady state experiment that gave us a better result. Finally, we want to thank our colleague Nicholas Blin for his work related with the development of the experiment of the unsteady state. Without his work and the quality of his data, this wouldn't be possible. Thank you, Nico, and thank you all.
Okay, thank you, Asier, for your presentation. And for the audience, please keep Q&A possibilities for questioning. Okay, then we continue with the next presentation, and the next presentation is done by Jonathan Jar Flores, University of Sao Paulo, and the title of his presentation is Wettability Changes on Rock Outcrop Samples and Synthetic Plugs with Mineralogy Similar to Carbonate Reservoirs. Jonathan is a petroleum engineer from Universidad Industrial de Santander in Colombia in 2015. He has a Master of Science in Petroleum Engineering from Universidad de Sao Paulo in Brazil in 2019, and he is currently a PhD student at the same university. He is currently also a researcher at INTRA, Integrated Technology for Rock and Fluid Analysis from University of Sao Paulo in the area of wettability and petrophysical properties of carbonate reservoir rock in Brazil. So, come on, Jonathan, we're looking forward to your presentation.
Good afternoon. On behalf of my thesis advisors, Dr. Jan Ferrari and Karina Wilson, we would like to thank you for being part of this presentation. Today, I will present to you about wettability changes on rock outcrop samples and synthetic plugs with mineralogy similar to carbonate reservoir. This research is part of a larger project that seeks the reproduction and study of synthetic plugs with controlled physical and chemical properties similar to reservoir rocks. Okay, so synthetic plugs formed in a laboratory are a viable alternative with controlled and representative rock characteristics where reservoir plugs cannot be extracted. Concerning the lack of publication focusing on forming synthetic carbonate plugs, a methodology was proposed and synthetic carbonate plugs were obtained successfully with controlled properties such as petrophysical properties and chemical properties such as mineralogy and wettability. This work focuses on a systematic investigation of wettability changes between synthetic plugs and rock outcrop samples with mineralogy similar to a carbonate reservoir by contact angle measurement before and after non-ionic commercial surfactant edge treatment. This with the main objective to obtain preliminary evidence which validates if synthetic plugs formed with this proposed methodology can be used as an alternative sample in a chemical IOR test such as a screen of surfactants. As I mentioned earlier, two kinds of samples were used to study wettability changes. Rock crop samples with a typical dolomitic mineralogical composition of calcium, magnesium, and silicon, and cylindrical shape dimension of 3.7 centimeters in diameter and 2 centimeters in height. And the other samples, two synthetic plugs composed of 100 grams of disintegrated dolomitic carbonate rock with controlled particle size. So one synthetic plug was composed by thinnest particle size and named F11, and the other composed by thickest particle size and named T11. Both samples were also composed of 5% weight-to-weight of emit wax used as a bonding material and 6% weight-to-weight of water content and pH 3 to promote desolubilization of the carbonate material, followed by its precipitation by applying temperature. Finally, it was applied an uniaxial compression with controlled loads and velocity to conform the synthetic plugs. Wettability alteration of rock outcrop samples and synthetic plugs were measured before and after 6 hours of aging treatment using non-ionic commercial surfactant mediums. 3 surfactants formulations were used in 4 concentrations, 50, 100, 500, and 1000 ppm. Contact angle measurements were performed on a drop shape analyzer equipment using the pendant drop method at room temperature and pressure. Distilled water droplets were placed on the flat surface of the samples, and the contact angle was measured after 10 seconds. The methodology consists of first measuring the contact angle of the rock outcrops before aging treatment, which is equivalent to the sample's natural wettability. Secondly, it was measuring contact angle of the rock outcrops after aging surface treatment. The wettability change behavior was evaluated, and one surfactant in one concentration was selected based on its efficiency. Then, it was measuring the contact angle of synthetic plugs before and after aging with the previously selected surfactant. Contact angles resulting from both outcrops and synthetic plugs aged with the same surfactant and same surfactant concentration were compared to understand the surfactant efficiency. From here, rock outcrops without surfactant aging shows an intermediate wettability similar to the literature reports of natural carbonate rocks from Reservoir, while after aging, the 3 surfactant mediums were able to alter the wettability from the initial intermediate wettability to water wet. This behavior was evidence for the 3 surfactants with the increasing of the surfactant concentration. Due to the low concentration compared with the decyl alcohol and lower decrease in contact angle compared with nonyl phenol, it was select isotriacyl surfactant at 100 ppm to be used on wettability tests of synthetic plugs. In this case, this surfactant at the select concentration showed an efficiency of 36.5% to change the wettability of rock outcrops compared with the sample's contact angle before the aging treatment. Concerning to the synthetic plugs, the same intermediate wettability was observed before aging treatment surfactant, followed by contact angle decreasing to water wet after aging surfactant treatment for both synthetic plugs, the one formed by the thinnest and the one formed by the thickest particle size. Also, surfactants change the thinnest plug's wettability by 35.7% and 35.8% to the thickest plugs. That is a similar efficiency compared to the 36.5% from rock outcrop aged by the same surfactant and surfactant concentration. So, this similar wettability behavior between rock outcrops and synthetic plugs is a promising result that shows a preliminary possibility of using these synthetic plugs with controlled properties, such as intermediate wettability similar to natural carbonate rocks regarding IOR tests, for example, in the screening of surfactants. Of course, these preliminary results will guide further dedicated wettability analysis to deeply understand this sample's property and enhance the construction of synthetic plugs more similar to natural rocks from carbon reservoirs. Okay, so we would like to thank the Escola Politécnica da Universidade de São Paulo and Partners Laboratory for the facilities and sponsor given to conduct part of this research. If you want to know more about synthetic plugs, please visit our startup website, Polyplugs. Here is my email too, please don't hesitate to contact me. Thanks, gracias, obrigado.
Thank you for the nice presentation. The next presenter is Jules Reed, working now at the Premier Oil Field Group, and the title of the presentation is Wettability Restoration: What, Why, Where, When, and even How. Jules joined Premier Oilfield Group earlier this year as a global technical manager, bringing almost 30 years of expert industry experience. He is the co-author of the authoritative book Core Analysis, a best practice guide V64 in Elsevier's Developments in Petroleum Science series, and is former president of Society of Core Analysts and currently sits on its technical committee. And I think the first time I met Jules was at the SCA meeting. Jules is an expert in most aspects of core analysis, with particular insights on wettability, capillary pressure, and relative permeability, and IOR. So the floor is yours, Jules. Looking forward to it.
Hi, my name is Jules Reed. I'm the Global Technical Manager of Premier Oilfield Group, and I was asked if I would speak on wettability restoration. So I've entitled today's presentation Wettability Restoration: What, Why, Where, When, and How. Potentially the only thing missing there is who, but the who is you, if you're going to be doing a wettability study and you're going to use wettability restoration. So as an introduction to my presentation today, I was wanting to look at the need to consider the whole process of core analysis. Consider it as a whole holistic process, because core analysis begins before coring. It begins about the decisions you're going to make in what the important aspects of the core are, because that can change the coring process, the coring fluids, etc. And then the preparative processes that we use in the laboratory can also influence our results. And so it's important to consider each of these steps. And I will be particularly going through what are we restoring, why, where, when, and how. So what are we restoring? In our book on best practices for core analysis, we propose that there's a order of best to worst type of core material to use in SCAL analysis or core analysis. The best is usually preserved core, whether that's whole core or core plugs, or even the carcass. This is a carcass, the remains of a core after it's already been plugged. Now, this may be somewhat changed depending on the fluids that have been used to cut the plugs. Then next best might be used core plugs. Sidewall core and slabbed core I'd be quite careful of using, and then entrance and cuttings depending on what you're going to be using for. The next question we have to ask ourselves is why? Why not use native states or as received, so that we're using the samples and the core material directly from the reservoir? And that's because there are changes that may occur. Temperature is reduced as we bring the core to the surface. That can change the solubility of components of our oil or our water. Those changes in the precipitation can also change then wettability. We also have pressure reduction, which can evolve gas from our system. And the evolution of gas can change, again, the solubility of things like asphaltenes. So that can then change wettability. We may also have oxidation of crude oils or our fluids, oxidation of the minerals, and that changes potentially wettability. We also have surfactants very often in our drilling fluids, and more this becomes a problem these days. And those surfactants will change the wettability. And so to use a core native state, we have to ensure that there's been no change, no saturation change, so therefore no mud invasion, no change to preservation, so no oxidation, and no asphaltene or salt precipitation, so that or if we do have that, we have to exchange those altered fluids for some controlled fluids, and therefore it's no longer really as received or native state. And more over the past 5 or 10 years, with the use of modern drilling fluids, low toxicity oils, with surfactants added to create emulsions to allow better wellbore stability, I've seen those impact scal studies creating samples that are quite heavily oil wet. This is one case where these samples here, after cleaning, are not water wet. They are mixed to strongly oil wet. And various attempts in the triangular data here to use different solvents, different cleaning techniques to try and get water wet conditions was unable without damaging the samples. Whilst a second well cut with a different fluid, it was able to get back to water wet conditions. The whole of this scal study had to be cancelled because of incorrect wettability, unrepresentative data. The next question is where? And what I mean by that is, where in the reservoir are we obtaining our representative samples? That requires understanding and characterizing our reservoir, looking at the different petrophysical groups, looking at saturation, because water saturation controls wettability. The more water you have present, the less likely you're going to have oil wetting, because the oil may not be able to cross the water film. We need to prepare then our samples to the same irreducible water saturation, or the same connate water saturation that we find in each of the different layers that we are studying in our reservoir. Our next question is when. And this is a slightly tenuous link. By when, I mean time. How long does it require to restore wettability? And this is still a big debate in our industry. It could be 6 hours for, say, a carbonate and a very acidic oil. It might be 6 days. I've seen a range of different times. 6 days, 12 days, 14 days, 28, 40. Generally, Anderson recommended 40 if you don't know what your wettability timing is, restoration time is. This paper by Skule and Scherland in 91, Wettability Symposium, also showed data as a function of time. So they performed spontaneous imbibition. This is the control of a water wet sample, showing that they had good water wet conditions initially, and then different aging times. So we had 12, 24 and 28 days in here, then 33 days, 38 days and 48 days. And there's a change throughout. It's generally becoming more oil wet or less water wet as time went on. We had one outlier which was at 42 days sitting up here, but in general the longer the aging time, the more oil wet or less water wet the data was. So that's still a question: how long does it require? And our last question is how are we going to restore? What methods are we going to use? And I'm not going to answer this directly because it can change depending on what your core is, what type of core you've been using, and its history, your reservoir history, and various other factors. So I would tend to suggest either miscible injection or submerged soxhlet as a potential process for cleaning. You need to consider what solvent choices you're going to use. The standard toluene methanol or chloroform methanol may not be appropriate, depending on your mineralogy. And you need to consider whether you're going to dry or not. Will drying cause problems for, say, water-sensitive clays like smectite? I would tend to suggest if you've got significant smectite present, then don't dry your samples. You may need to go straight to saturation, and that would be miscible saturation, so that you would, from, say, a methanol finish to cleaning, you would miscibly inject with your formation water, obviously checking that there's no precipitation from mixing of those fluids. Otherwise, if you think you can dry the sample, then measure the basic gas properties, ensure that they tie in and correlate with previous reservoir data, and then after saturating the samples, you would then use vacuum and imbibe water under vacuum and then pressurize and then check that it's 100% saturated. After you've obtained saturated samples, then measure water permeability. And if you've gone straight to saturation without drying, then you may need to do, say, a dispersion test to determine the pore space of the sample. And quality control again. Just make sure that your data makes sense, that they correlate to each other, so that gas permeability agrees with water permeability. If not, you've got potentially unrepresentative samples. You will then establish SWI, and I would suggest or recommend that porous plate is the best technique for that. It gives you an even distribution of fluids across your sample, apart from heterogeneity, but then you should have selected a homogeneous sample right at the start. Centrifuge would be the next best, but it will potentially have saturation gradient because you have a pressure gradient from the centrifuge. And flooding is really the worst technique for establishing SWI, but sometimes it's the only way of performing it, because you cannot get the pressures required to get to SWI. And your SWI really should match the height in the reservoir and the reservoir SW data of that height as you prepare wettability. You also need to consider what fluids you're going to use to establish SWI. Live oil, which usually will be the best oil to perform wettability under and to restore under, may not be available, or may not be available for the technique you're using. So you may need to use gas or lab oil. And if you're going to use gas and lab oil, you need to then change from that fluid to your dead oil or your live oil. And that may require buffering from something like Decalin to try and prevent asphaltene deposition. And once you've got to SWI, you then need to quality control again. Does the SWI match my data? Does effective permeability at SWI match my data? And do they correlate? So in this particular diagram here, these look like outlier data. They're significantly different than the major data. So there are 7 samples here. Are these outliers, or is this a different rock type? And you need to make those considerations before going forward. And also, what aging technique will you use? There are 3 main ones: static, dynamic in a single direction, and dynamic in both directions. And there was this paper by Johansson et al. In 2008 showing the impact of these different techniques. So static, you could have a slight wettability gradient from the outer edges of the sample into the middle. If you're only using unidirectional dynamic flooding, then you will get a gradient across the sample in the direction of flooding. And also, if you use a bidirection, you change the direction, you get a more even distribution of wettability. And also the oil volume. How much should I be using? This has become a debate in our industry of what volume of oil should I use in changing wettability. And what I've heard that some say, well, we only use one pore volume. But if you consider the charge point as oil came into the reservoir, it came into maybe some point. We don't know. This is why the history is important. But as it goes through the reservoir, then different distances from the charge point will observe different pore volumes of injection. So at the extremities, maybe only one pore volume, maybe less than a pore volume. But as you get halfway, it will be double the volume at the extremities. And as you get closer and closer to the charge point, you have tens, maybe hundreds of pore volumes of throughput. So you may need to consider this to consider what is my average throughput. And so to summarize, when we're looking at aging, we need to consider a holistic approach. That must consider our material provenance. So what's the history of a material? It needs to mitigate against potential alterations from coring, from handling, and from preparation. We need the material to be representative, and that requires then quality control of our process and of our data matched to a reservoir data, and appropriate methodology and quality control of those methods as well. Thank you for your time.
Yes, hello again, and thank you all presenters for nice talks and presentations. So let's have some discussion and some answer to some questions. And if Asir, if you are there and can unmute your microphone, that would be nice.
Hello.
Hello. Can you hear me well?
Yeah.
Yes. So thanks for the nice presentation, very interesting. And we have a couple of questions. The first question from studio. So what kind of rock material is representative for the shown results? And how do you think mineralogy will affect your simulation studies?
The work we have done, it has been with carbonate rocks, different rocks in each of the cases. And for sure, when we are analyzing the relative permeability, we know it's a system that we have three different. The system depends on the rock, the brine, and the oil. For sure, if the rock changes, all changes. No, so it's something that must be done for a specific system, and if one of them changes, you should redone your work. No, it's a specific of a rock, brine, oil system. So yeah, for sure.
Yes, thank you. And another question was in the relative permeability curve, the starting KRO, the relative permeability for oil, for the measured data and simulated data were very different. So can you explain this large mismatch?
Yeah. Well, as I explained, what we had in that experiment in the laboratory data was there were measurements of the mass balance. So all the saturations that we obtained, that was that average value that we talked. Then when we did the simulation, we realized that we had that end effect, and that corrected our saturations. So there is a gap between what the simulation, which is the maximum water saturation that is achieved by simulation, and the one that we measure. That explains how the both curves have been displaced in the simulation part, increasing water saturation, because the water saturation that is without that end effect is greater than what we measure at the laboratory. So that is a correction for that.
Yes, thank you very much for a detailed answer, and thank you for your presentation once again. And I would like to ask a few questions to Jonathan. So if you're there and can unmute your microphone.
Hello.
Hello, hello. So can you hear me well?
Yes.
Yes, very nice. Thanks for your presentation once again. And I have a few questions which I wanted to ask you. So the question was like, can you explain more about synthetic cores? By which method you fabricate them? Do you see any materials to fasten? Do you use any materials to fasten or using compaction? And what are the range of porosity and permeability for the cores? And what's the potential cost of making this synthetic core?
Okay. First, thank you for the opportunity. About the construction of synthetic plugs, it was used an uniaxial compression with controlled load force and velocity. In addition, it was used bonding materials based on a wax acid in a low concentration just to have a better consolidation. In order, and it was used to the solubilization and precipitation of the carbonate-based material by using an acid pH and high temperatures, just to have the solubilization first by the acids solubilization, and then the precipitation of the material by using the high temperature. So this was the main point to construct the synthetic plugs. Responding to the second part of the questions about concerning the porosity and permeabilities, now we can construct synthetic plugs with a porosity from 10% to 19% and permeabilities from 0.07 to 0.7 millidarcies. That is a great kind of range about porosity and permeability. For example, here talking about the carbonate pre-salts from Brazil. That is all.
Yeah, so I guess that was a good answer. And okay. I have one more question. So the question was, did you try to quantify the effect of different wettability states of your cores on the effect of wettability alteration using different surfactants? How were the surfactants chosen for this study?
Okay, so the surfactants was selected by using a non-commercial, a non-ionic commercial surfactant that is used in some carbonate reservoirs to enhance the production. So at this point of the research, we didn't study the wettability and difference points, but this part of the work that was presented here. It's just the first part of wettability studies that we are going to develop in the whole study. So we pretend to have some specific or dedicated petrophysical and wettability tests in this kind of synthetic plugs.
Yes, thank you, Jonathan, for the nice answers, and thanks for presentation once again. Thanks for joining us. And then I would like to move to our last presenter, Jules. Yeah, so I'm not sure if I pronounce names correctly. I'm sorry. So can you hear me?
Yes, I can. Can you hear me?
Yes, we can hear you as well. Well, thank you for all actually very nice and detailed presentation. It's very interesting studies. And we have a couple of questions to you. So the first question was, was there any comparative study performed on the degree of wettability restoration using dead oil, live oil, and surrogate lab oil with similar EACN to live oil? And how do you think the mineralogy of sandstones affect the wettability restoration process in your opinion?
So to the first question about the use of oil, there are some studies over the years that have been done comparing dead oil to live oil. Some of those show that there's significant difference, and some of them show that they're quite similar. And often it's a case of the gas content. So where you have a high GOR oil, and as you bring that to surface, so that your oil may look, when it's live, if you are able to observe it in say a visual separator, under reservoir pressure and temperature, you will see that it's quite light, maybe translucent, but the dead oil, because you lose all the gaseous portions, you're left with the heavy sections, which often contain all of the most of the polar wetting components, and it may the dead crude may appear very dark and quite viscous compared to your live oil, and so then in terms of a volume, polar components versus volume of oil, you've got much higher levels of polar components in then the dead oil. So a number of there's no real fixed point. A number of the companies have a sort of suggested cutoff point, which might be something like 40 cubic meters per cubic meter of gas content. That anything above that, your dead oil does not represent your live oil. I haven't seen many, that could be just I haven't found the literature on surrogate oils. I have done studies in the past where we've added in additional, say, alkanes and alkenes to try and bolster the oil volume to reduce the resin or asphaltene composition and try and get back to a similar mass weight compared to my reservoir oil, using some of those synthetic components or standard components, like adding methane in or so on. There aren't I haven't seen a lot of information on that, because normally if you're having to do that, it's because you don't have live oil samples or a sufficient sample volume to use against it. In terms of how do I think the mineralogy of sandstones affects wettability restoration? Well, in sandstones, we believe that the minerals are the wetting component. I have a picture I use in a wettability webinar that shows a pore space. You can clearly see a quartz grain where the quartz grain is water wet. You have a droplet of water, which is a very low angle curvature on that droplet. And there are some mixed clays, and those clays have a fluid across the top of them, the surface of them, and a water droplet on them, where the water droplet is clearly non-wetting. It's sitting as almost a perfect droplet on it. And that it's an SEM. The EDS or spectroscopy of the EDS allows you to see what the composition of the fluid on the surface of the minerals was, and that was a hydrocarbon. So in that particular case, it was the minerals were hydrocarbon wetting and the quartz was water wetting, and that's it within a pore space. So this wettability is much more complex than saying it's water wet or oil wet or just a contact angle. Our contact angles are a mix of many different contact angles, a distribution of contact angles depending on the surface that the fluids are touching and what fluid is wetting.
Thank you very much. I think we have time for the last question before we end up. And it's more like a rhetorical question, I would say. So if you receive the core sample without knowledge of the drilling conditions, location, and so on, and would like to study oil recovery on them, what would be your best shot on wettability restoration?
So usually the drilling conditions are not unknown. It may require a little bit of digging, questioning the oil company who's asking for the study, finding out where they were drilled and what they were drilled with. There will be end of well reports. And of course, if you were going back many years, then maybe the data has been lost, or people can't find it. So sometimes it's difficult to find, but usually the data is there somewhere. But it's really a case of just trying to get as much data on the reservoir as you can that is available, and that could be logs, or it may be previous core data, and trying to just go through those steps, preparing the core in each of the steps, quality controlling your data at each step, and making sure you've got data that agree with one another and agree with any previous data that you have.
Thank you very much. So you have one more question, but unfortunately we should move towards the ending of the session. So maybe if you can reply to the question in the chat, that would be great. So thank you very much once again for the presentation, and thanks to everyone. So I would like to thank for Tina and Skule for the opportunity to be part of this Wettability Symposium and be able to talk to different clever people. So then I'm moving, and Tina, floor is yours. Thank you.
Thank you, Alex, for this taking care of all the questions for us. Really, really helpful. So now, first I would like also, of course, to thank everyone for the good discussions. And of course, many of us would maybe like to continue for a few more hours. But our time is running out, and we need to wrap up this symposium. So, Skule, how would you summarize the symposium today?
I think Jules, in a way, summarized the Wettability Symposium in a way quite good. And what we are really working with when we're talking about reservoirs and wettability, it's complexity, and definitely. So if you're going to understand reservoir wettability, we need also to take into account all the individual phases present in a reservoir. And the reservoirs consist of a brine phase, it consists of a mineral phase, and it consists, and generally water brine initially before the oil phase migrated into the reservoir. I think most of the reservoirs are very water wet. So it's not exactly as you said. It's the it's the oil and the components in the oil that change wettability through the migration and accumulation in the reservoirs. And we can always discuss how many pore volumes certain areas of the reservoirs have seen. But as a totally, if you look at the reservoirs, most reservoirs have only seen 1 minus SWI of oil. So far less than 1 pore volume with oil. And when we are discussing how to restore core material, definitely we need to have that in mind. So generally, if you are using centrifuge, or if you are using flooding of cores, if we expose the core material to several pore volumes with crude oil, definitely that can affect our core restoration process. But if you look more into general all over, we started the day today with a more fundamental approach, and going from surface complexation and modeling, trying to understand mineral polar components interaction that we can link to wettability, and definitely I think it's the polar components in the crude oil that behaves as an anchor molecule on the mineral surface and are wetting the surface. And if there is an oil film or not present, I think that we will probably, if we could go 100 years forward in time, we will probably still be questioning the same problem. But it's these anchor molecules that are, in a way, the molecules that also need to be desorbed, or we need to unstick from the mineral surface if we're going to change wettability. And smart water EOR process has definitely been a huge discussion around. During the last 20 years. It was Norman Morrow who started it, same guy who started the Wettability Symposium, because I think he saw the need of understanding wettability, because it influenced his research. And I think it was a good idea, because wettability is something that we probably can do research in and discuss for the next 100 years. And probably we are not having the answer yet. Hopefully we are a little bit closer to the correct answer. And then definitely electrokinetics and streaming potential if we want to link surface charge to wettability is also an important part. Is it the polar positive? Is it the acidic polar components in the crude oil that affect the wettability, or is it the basic components? And surface charge is definitely important. And what we have seen in the research work on chalk, we see that it's the acidic components that are by far most active towards the mineral surfaces. So, while when we are working with sandstones, generally silicate minerals are on the negative sides when we are talking about surface charges, and on the negative charge, it's the positive polar components, or the basic polar components that are present in the crude oil that seems to influence the wetting the most. If asphaltenes and asphaltene precipitation is something, definitely it will affect the wettability, but are we able to desorb it or dissolve it back into a liquid phase in the reservoir? I don't believe it. So for me, if the reservoir wettability is controlled by asphaltene precipitation, we are stuck with that wettability. That's my opinion. Everyone, all the audience are allowed to have their own opinion about it. And then we had a little bit look into the importance of capillary forces. How much does the capillary forces affect the mobilization of oil in porous media? And I think that's something that we have forgotten in the modeling approach with applying Darcy's law and looking at relative permeabilities and try to define that. Is viscous forces that important in oil drainage? I'm just putting up the question. There are indications that definitely the smart water EOR approach definitely see that capillary forces is definitely active in the mobilization of oil and lowering the residual oil saturation. So it needs to be accounted for. If it's account for 90% of the oil, or it's only account for 30% of the oil, I don't have the answer on that. But if you ask me, I could always say that I think it's more than 30%. I think it's the main driving mechanism in the reservoir, as long as the reservoirs are on the water wet side. So there is definitely a difference between, and people are often talking about oil wet or water wet reservoirs. It's nothing called water wet or oil wet. There are a mixed wetting that are present. If it's a dalmantine but definitely if you look into the different type of minerals that we have in reservoirs, definitely there are different minerals have different affinities towards polar organic components. So to believe that we can have a homogeneous wetting into the reservoir, I don't believe in that. So And definitely, back to what we have looked into, wettability and core restorations is definitely important if you are going to replicate reservoir wettability. And what we saw from one of the presentation, if we add more crude oil into the core system, we lowering the initial wetting. So when we are designing the optimized core restoration processes, we need to be aware of how much oil we expose to the mineral surface. In the same way as there was a question regarding earlier today regarding contact angle measurements. If you are doing contact angle measurements on a 1 square centimeter of surfaces and we add a huge amount of oil to that surface, it's not realistic, it's not comparable what's happening in the reservoir system. So in the reservoir system we hardly have liquids, but we have a huge amount of surfaces. And if you look at bed analysis, it's not unnormal that we have 2 square meters of rock surfaces for 1 gram of rock. 2 square meters. It's a few droplets of liquid that is going to be spread over a surface of 2 square meters. And definitely back to what ending with what we started with, definitely to have the experience and the knowledge of people who have been working with rock, with core material and in laboratory facilities, optimizing core analysis is important, and definitely also the mud contamination and these processes, it's definitely the cores that they are received to the laboratory is not necessarily native state, and we need to understand the processes taking place. I think that's the wrap up, but what I believe is that we have had a lot of good questioning from the audience. I think it's been very good questioning. It's not always that easy to understand a presentation coming in a few minutes, and it's a lot of specialized work and good specialized work from individual researchers, and definitely it's a good opportunity for everyone to learn, and I think that there was a lot of good questioning to the presenters, and I will thank all the presenters for putting up all this and doing this work to make good presentations, and we are really happy with that.
Thank you, Skule, for your views on today and for your always interesting opinions. Then, before we end this 14th symposium, I would like to announce that the next symposium, the 15th one, will most likely be held in Laramie in Wyoming. I have been in contact there with Professor Mohammed Piri, and he would love to host the next wettability symposium there. So back in 1994, actually the third wettability symposium was held in Laramie, Wyoming by Professor Norman Morrow, who we have heard quite a few. We have heard about him quite a few times today. So we are looking forward for the next symposium in Wyoming, hopefully in 2022 or 2023. Again, as Skule said, we would like to thank all the speakers for their contributions and all the guys in the audience for your questions. And I would like to thank also Alex, who has managed all your questions in a very good way. And hopefully we'll see you somewhere soon in a real symposium where it's not digital, but everyone is present and presenting live. But I think that today went really well. Even though it's a digital session, I think it was very interesting day with very good presentations, and some discussion back and forth actually was possible also. So I'm pleased with today.
Yeah, here in the studio we have had a nice day at least.
Yes. So hopefully see you somewhere soon. And don't forget to connect tomorrow for the IOR Norway 2021. And have a good day. Have a good evening and have a good night.